In the year 2017, scientists announced the discovery of Earth's newest continent. This hidden land, called Zealandia, had long been thought to be part of Australia, but it was officially recognized as its own separate continent. Zealandia originally split away from the ancient supercontinent Gondwanaland about 85 million years ago. When it drifted off, many dinosaurs and sea reptiles like mosasaurs and plesiosaurs went with it. That was only the start of its journey, as the land kept changing and slowly became what we now know as Aotearoa, New Zealand. Before we start, let us know in the comments below where in the world you're watching from and what time it is for you now. So, get ready for a fascinating journey to the prehistoric times on Earth. Long ago, our planet was not shaped as it is today. The continents we recognize now as separate lands were once joined together in vast supercontinents that stretched across the face of the Earth. One of these ancient giants of land was called Gondwanaland. This supercontinent was a massive union of territories that included what we now know as South America, Africa, Antarctica, Australia, the Indian subcontinent, and a long and mysterious piece of land that today is largely hidden beneath the Pacific Ocean. That hidden land is what scientists now call Zealandia. Zealandia is not just a small island chain or a cluster of fragments. It is, in fact, a continent in its own right, though most of it now lies beneath the waves of the sea. The land we see today as New Zealand and New Caledonia are simply the mountaintops and higher ridges of this immense sunken continent. The greater mass of Zealandia remains submerged, stretching over an enormous area that covers nearly 5 million square kilometers, making it almost as large as the continent of Australia. Despite being hidden for millions of years, it has a long and fascinating history that links back to Gondwanaland and to the times when dinosaurs still roamed the Earth. To understand Zealandia, it helps to journey far back in time, more than 180 million years ago, when Gondwanaland itself began to break apart. In those ancient days, the Earth was a very different place. The world was warmer, the seas were higher, and great reptiles ruled the land and the oceans. Gondwanaland had existed for tens of millions of years as one of the great continental masses of Earth, but it was never to last forever. Beneath the surface, the forces of plate tectonics, those slow but unstoppable movements of Earth's crust, were preparing to pull it apart. These hidden forces are what ultimately gave birth to Zealandia. For tens of millions of years, Gondwanaland began to fragment. Pieces of land drifted away from one another, carried slowly across the planet by the vast slabs of rock called tectonic plates. The landmass that would later become Zealandia remained attached to the edges of Australia and Antarctica for a long time, but pressure built beneath it. About 85 million years ago, a dramatic change began. Zealandia began to separate from Gondwanaland, moving northeastward, while Australia and Antarctica drifted in different directions. The process was slow in human terms, but on a geological scale it was rapid and profound. At the time when Zealandia began its lonely voyage away from Gondwanaland, the world was alive with creatures unlike any we know today. Dinosaurs roamed the land in great variety, while the seas were filled with enormous marine reptiles like mosasaurs and plesiosaurs. Birds were only just beginning to take their early forms, and flowering plants were spreading across the continents. Zealandia was not empty. It carried with it ecosystems of its own, with forests, rivers, and plains that supported life. Though scientists still debate the full range of animals that lived there, fossils reveal that at least some dinosaurs once walked the surface of Zealandia, along with the flying reptiles that soared above it. As Zealandia drifted further from Gondwanaland, its fate was sealed not as a high and proud continent like Africa or South America, but as a land that would slowly sink beneath the sea. Its crust was thinner and lighter than the great continental plates that carried other lands, and over time, as the forces of Earth stretched and pulled at it, much of Zealandia lowered beneath the surface of the ocean. Unlike Australia, which rose as a vast landmass, Zealandia became a hidden continent, leaving only its highest ridges above water. Those ridges are the islands we now call New Zealand, New Caledonia, and a scattering of smaller islands in the Pacific Ocean. The sinking of Zealandia was not sudden but gradual, occurring over tens of millions of years. Imagine a land full of mountains, valleys, forests, and rivers slowly being drowned as the sea crept higher and higher. Hills became islands, valleys became seabeds, and what was once an expansive continent became concealed beneath waves. Yet, even as most of Zealandia sank, it did not vanish. The land remained there, solid rock beneath the waters, with mountains, plateaus, and ridges shaping the seafloor in patterns that echo the hidden outline of a continent. For a long time, people did not know Zealandia existed. Polynesian navigators who reached New Zealand many centuries ago knew only of the islands that rose above the waves, and to them, those lands were entire worlds filled with forests, mountains, rivers, and rich coastlines. European explorers who sailed into the Pacific in the 17th and 18th centuries likewise saw New Zealand and New Caledonia as distant islands at the edge of the world, without any notion that they were part of something far larger. It was only in the late 20th and early 21st centuries that scientists pieced together enough evidence to declare Zealandia a true continent. This recognition came in the year 2017, when a team of geologists formally announced that Zealandia was not merely a collection of islands, but a continent nearly as large as Australia. They pointed to geological evidence showing that Zealandia has all the qualities that define a continent. It is a large, distinct mass of continental crust, separate from Australia, with its own geology, structure, and history. Though most of it lies beneath the ocean, its unity as a landmass cannot be denied. With that announcement, Earth gained what some called its eighth continent. The idea that a continent could remain hidden beneath the sea might sound like a tale from legend. Yet, Zealandia is entirely real. Its discovery shows us how little we still know about our planet, and how the boundaries of land and sea are not always as simple as they appear on maps. Zealandia invites us to rethink what a continent truly is. While we often imagine continents as high and dry lands where people build cities and civilizations, the definition is actually about the structure of Earth's crust. By that definition, Zealandia qualifies fully, even though the sea now covers most of it. The history of Zealandia is also tied to the history of New Zealand itself, which sits upon the peaks of this sunken continent. The mountains, fjords, and volcanic landscapes of New Zealand are shaped by the same tectonic forces that once tore Zealandia from Gondwanaland. Earthquakes and volcanic eruptions still shake the islands, reminding us that this land rests on the dynamic boundary between the Pacific Plate and the Indo-Australian Plate. Beneath the sea, Zealandia's hidden mountains and ridges continue this pattern, shaping the seafloor into dramatic forms. For scientists, Zealandia provides an extraordinary opportunity to study Earth's geological past. By drilling into seabeds and collecting rock samples, researchers have uncovered fossils and sediments that tell of ancient climates, lost ecosystems, and long-vanished creatures. These findings help us understand not only Zealandia itself, but also the wider processes that shaped Gondwanaland and the modern world. Every fossil leaf, every ancient shell, and every buried layer of sediment is like a page from Earth's history book, preserved under the ocean for millions of years. The recognition of Zealandia also stirs the imagination. To think that a continent nearly as large as Australia lies almost entirely beneath the sea makes one wonder what else remains undiscovered on our planet. If such a land could remain hidden until modern science revealed it, perhaps other secrets still wait beneath the oceans, which cover more than 2/3 of Earth's surface. The oceans are vast, deep, and largely unexplored, and Zealandia is a reminder of their mysteries. In human culture, the idea of a sunken land has long fascinated people. Legends of Atlantis, the fabled lost city beneath the waves, echo the reality of Zealandia. Though Zealandia is far older and far larger than any legend, unlike Atlantis, which is a myth, Zealandia is supported by science and geology, yet its hidden nature gives it an almost mythical aura, as though the Earth itself holds secrets that reveal themselves only with patience and study. One can imagine Zealandia in its prime tens of millions of years ago, when it stood above the sea as a vast and living land. There might have been forests filled with strange plants, rivers winding through valleys, and plains where dinosaurs grazed. The skies may have been crossed by flying reptiles, and the coasts may have been lapped by seas where marine reptiles hunted. It was a world now lost beneath the ocean, but not lost forever, for its memory is preserved in rock and fossil, and its outline can still be traced beneath the waters. When we look at the surface of our planet today, it is easy to believe that the continents have always stood where they now rest. The vast outline of Africa, the broad expanse of South America, the enormous sweep of Asia, and the wide lands of Australia and North America feel permanent, like the natural and unchangeable shape of the world. Yet the truth is far more dynamic and filled with movement. The surface of the Earth floats on restless plates of rock that slowly slide, collide, and separate. These great blocks of crust and upper mantle, called tectonic plates, shift like pieces of a puzzle that never truly locks into place. Over hundreds of millions of years, they create and destroy oceans, raise mountains, and scatter entire continents across the globe. Among the most fascinating of these movements is the long and dramatic journey of a hidden continent called Zealandia. For most of human history, no one even realized that such a continent existed because nearly all of it lies beneath the waves of the Pacific Ocean. Only a few high points rise above the sea, the islands of New Zealand, New Caledonia, and several smaller scattered island chains. Beneath the surface, however, lies a vast, drowned continent that once had a different fate. To understand what happened to Zealandia, we must return deep into the past, to a time when the world was ruled by dinosaurs and when the great supercontinent Gondwanaland stretched across the southern hemisphere. Gondwanaland itself was formed long before Zealandia's story reached its turning point. It was born out of the slow merging of earlier continental masses during a period that began hundreds of millions of years ago. By about 500 million years ago, most of the southern lands of Earth were united in this colossal continent. Gondwanaland contained what we now recognize as South America, Africa, Antarctica, India, Madagascar, Australia, and of course the landmass that would one day become Zealandia. At its height, Gondwanaland was a giant that covered much of the planet, stretching from the equator to the icy reaches of the South Pole. Life thrived across this supercontinent in different forms during different eras. Forests of strange plants blanketed the land, rivers cut across wide plains, and swamps hosted amphibians and reptiles. Later, during the age of the dinosaurs, Gondwanaland became home to some of the most incredible creatures that ever lived. Enormous long-necked sauropods, fierce predators, and early birds all roamed its landscapes. But even as life flourished, deep inside, the Earth's forces were building that would eventually tear this giant continent apart. The split that concerns us here began in the late Cretaceous period, around 85 million years ago. At that time, dinosaurs were still walking the Earth. The seas were filled with marine reptiles like mosasaurs and plesiosaurs, while early flowering plants were spreading across the land. The world looked familiar in some ways, yet also profoundly alien. What made this period especially important for Zealandia was that the landmass began to drift away from Gondwanaland. The process did not happen suddenly. Continents do not separate with a single crack like a stone breaking in two. Instead, the movement is slow, almost invisible when measured by human lifetimes, yet unstoppable when measured by geological time. It begins with forces beneath the crust. Heat from the Earth's interior causes convection currents in the mantle, which puts stress on the overlying crust. When enough pressure builds, the crust begins to stretch and thin. Faults form, rifts open, and eventually new ocean basins are created as molten rock pushes upward. This is what happened between Zealandia and the rest of Gondwanaland. The land that became Zealandia was once attached to the eastern edge of Gondwanaland, near what is now Eastern Australia and Antarctica. Around 85 million years ago, the crust beneath this region began to thin. Slowly, Zealandia started to pull away. It was like watching dough being stretched apart until a gap forms. The gap widened, seawater flooded in, and over millions of years, a new ocean floor was born between Zealandia and Australia. This was the Tasman Sea, which today still separates New Zealand from Australia by more than 2,000 kilometers. During this separation, Zealandia itself was not broken into small pieces, but drifted away as a single large mass. Geologists now know that Zealandia is about 2/3 the size of Australia, making it a true continent by scientific definition. It has its own geology, its own crustal structure, and its own history. However, unlike other continents, much of Zealandia is unusually thin and light, which made it prone to sinking. As it moved away from Gondwanaland, parts of Zealandia began to subside beneath the waves. Slowly but surely, the continent disappeared below the ocean's surface, leaving only its tallest ridges and mountain chains above water. These are the islands we know today. The drifting of Zealandia had many consequences, not only for geology, but also for life. When the land separated, it carried with it ecosystems and species that were cut off from the rest of the world. Dinosaurs that lived in Zealandia became isolated, as did smaller animals and plants. This isolation would shape the unique character of New Zealand's wildlife millions of years later. For example, the ancestors of flightless birds, such as the kiwi and the moa, may have roots stretching back to these times when Zealandia was a distinct land separated from its parent continent. Imagine the scene during those ancient years. Forests of conifers, ferns, and cycads covered Zealandia. Rivers and lakes dotted its surface. Herds of dinosaurs wandered across valleys, while flying reptiles circled in the sky above. Along its coasts, giant marine reptiles hunted in the warm, shallow seas. Then gradually, the land began to sink. Low plains became swamps, swamps became lagoons, and lagoons were swallowed by the encroaching ocean. The mountains remained, but the rest of the continent slipped beneath the surface, hidden but not destroyed. The drifting away of Zealandia also helped to shape global ocean currents and climate. When continents move, they change the flow of water around the globe. The opening of the Tasman Sea altered the circulation of the Pacific and Indian Oceans. Over tens of millions of years, these changes would influence weather patterns and the distribution of heat across the Earth. In this way, the story of Zealandia is not just about one continent, but about the entire planet and its interconnected systems. Scientists pieced together this story through many decades of research. For a long time, Zealandia remained hidden in plain sight. Sailors and explorers saw the islands of New Zealand, but they did not realize that beneath the waves stretched an entire continent. Even geologists hesitated to use the word continent because so much of it was submerged. Only in recent decades, with new technology and detailed mapping of the ocean floor, has the true extent of Zealandia been revealed. Seismic studies, rock samples, and gravity measurements all confirm that Zealandia is not just oceanic crust, but continental crust, similar to the crust that makes up other continents. It has granite rocks, sedimentary layers, and volcanic chains that mark it as part of a continental mass. These discoveries have reshaped our understanding of Earth's history. They show that continents can be drowned, yet still survive as distinct geological entities. The timing of Zealandia's separation is also important for understanding the evolution of life. By 85 million years ago, the dinosaurs had already flourished for tens of millions of years. The breakup of Gondwanaland scattered them across isolated land masses, which led to unique evolutionary paths. In Zealandia, isolation meant that some creatures survived while others vanished. When the Great Extinction at the end of the Cretaceous period struck about 66 million years ago, wiping out the non-avian dinosaurs, Zealandia was already deep underwater. The ecosystems that had once covered its plains and valleys were gone, yet the land beneath remained, waiting to one day be rediscovered. To make sense of the scale of time, think of it this way. 85 million years is so vast that if one counted a single year every second without stopping, it would take more than 2.5 years just to count to that number. That is how long ago Zealandia began its journey away from Gondwanaland. During that time, mountains have risen and worn away, oceans have opened and closed, and countless species have evolved and gone extinct. The Earth we know today is only a snapshot in a long and ongoing story of change. In human terms, the recognition of Zealandia is incredibly recent. It was only in the year 2017 that a group of geologists formally declared it to be Earth's newest continent. They argued that it meets all the necessary criteria. It has well-defined boundaries. It is made of continental crust. It is elevated above the surrounding ocean floor. And it has a large enough area to count as a continent. With this declaration, Zealandia joined the ranks of Earth's continents, though it remains largely hidden beneath the sea. The drifting of Zealandia also raises intriguing questions about the future. Continents continue to move today at the rate of a few centimeters per year, which adds up to thousands of kilometers over tens of millions of years. Australia, for instance, is slowly moving northward toward Asia. One day, far in the future, new supercontinents may form as today's continents merge again. Perhaps Zealandia, now mostly submerged, will one day collide with another landmass or rise again through tectonic forces. The planet is never still, and the story of Zealandia is still unfolding. When we think about Zealandia drifting away from Gondwanaland, we should not imagine it as an isolated event, but as part of a much larger cycle of continental drift. Gondwanaland itself had already begun to fragment long before Zealandia's departure. Africa split from South America, opening the South Atlantic Ocean. India broke away and drifted northward to eventually collide with Asia, forming the Himalayas. Antarctica remained near the South Pole, while Australia moved northward on its own path. Zealandia's separation was one chapter in this grand saga of moving continents. Each piece carried with it traces of ancient life and geological history. The land that we now call Zealandia is special not only because it sank, but also because it continues to shape the culture and imagination of the people who live on its surviving islands. The Maori of New Zealand have long spoken of a great land beneath the sea, and modern science has, in many ways, confirmed that ancient vision. The recognition of Zealandia as a continent has also given new meaning to the uniqueness of New Zealand's landscapes, which are the visible peaks of a hidden giant. As we reflect on what happened 85 million years ago, it becomes clear that Zealandia's journey is both a geological and a biological tale. It is about the slow tearing apart of crust, the flooding of land by oceans, and the survival of fragments that still rise above the waves. It is about isolation, extinction, and the possibility of renewal. And it is a reminder that our planet is alive with movement, constantly reshaping itself in ways that are both subtle and dramatic. Even now, as scientists continue to study Zealandia, new discoveries are being made. Drilling projects into the ocean floor have recovered sediments that reveal ancient climates and ecosystems. These sediments tell us that Zealandia once lay in warmer waters and supported rich forests. Fossils of plants and animals, including those of dinosaurs, hint at the life that thrived there before the seas rose. Each discovery adds another piece to the puzzle, helping us understand not only Zealandia's past, but also the processes that govern all continents. The separation of Zealandia from Gondwanaland was, therefore, not simply a geological event. It was the beginning of a new chapter in Earth's history, one that shaped ocean currents, influenced climates, and set the stage for unique evolutionary pathways. The world we see today is the product of endless movement, and the future will bring even more transformations. When people today hear the word dinosaurs, they often think of mighty creatures that once ruled the land, enormous beasts with teeth, claws, and bodies so large they seem almost like something from another world. They imagine the well-known giants like Tyrannosaurus rex or the long-necked Brachiosaurus walking through great forests, or smaller but quick predators racing across plains in search of prey. What is less well known is that these animals lived not only on the famous lands of North America, Asia, and Africa, but also on a continent that for a very long time remained hidden beneath the ocean. This continent is called Zealandia, and it may have been a refuge for certain species of dinosaurs. A safe haven where they managed to survive while, in other places, their world was beginning to change. To understand why Zealandia might have served as a refuge, it is important to go far back in time to an age when the continents of Earth were not arranged the way they are today. Many millions of years ago, long before humans ever appeared, most of the land on Earth was joined together into a supercontinent known as Gondwanaland. This immense landmass stretched across the southern part of the globe, joining what would one day become South America, Africa, Antarctica, Australia, India, Madagascar, and the great hidden continent of Zealandia. Life thrived across these vast lands, and among the most successful creatures were the dinosaurs, which came in many shapes and sizes. Gondwanaland gave them space to spread and adapt, and for countless generations, they flourished there. But the surface of Earth is never still. Beneath our feet, the crust floats on molten rock that slowly shifts, dragging the continents along like rafts on a restless sea. Over time, Gondwanaland began to break apart. Each piece drifted away, forming the continents we know today. Zealandia was one of those pieces. Around 85 million years ago, this large fragment began to separate from the rest of Gondwanaland, slowly pulling away from Antarctica and Australia. As it moved, much of it began to sink beneath the ocean, but parts of it remained above the water, forming the lands we know now as New Zealand and New Caledonia. These surviving islands were not just scraps of land. They were homes, habitats, and possible sanctuaries for the life that had been carried along when Zealandia broke free. Imagine a group of dinosaurs living in what is now eastern Gondwanaland. As Zealandia slowly drifted away, those dinosaurs and many other creatures would have found themselves stranded on a new land mass. They did not cross vast seas. Rather, the sea spread around them as their land pulled apart from the greater continent. This accidental isolation created something like a natural ark, a floating refuge carrying with it plants, animals, and ecosystems. Once separated, the creatures of Zealandia were cut off from their relatives on other lands, forced to survive in a world that was changing all around them. This isolation could have allowed some species to survive longer here than elsewhere, shielded by geography and by the unique conditions of their environment. It is easy to imagine why Zealandia might have been a refuge. Dinosaurs and other animals elsewhere faced new dangers as the continents shifted. Changing climates, new predators, and rising seas may have threatened them. But in Zealandia, creatures had a kind of natural fortress. Surrounded by wide oceans, they were protected from some of the competition and predators that developed on other continents. The environment may have been more stable for a time, with forests, rivers, and coastal regions providing food and shelter. For species struggling to hold on in other regions, Zealandia may have offered safety. Scientists have found evidence that dinosaurs did live in what is now New Zealand during the age of dinosaurs. Fossils of creatures such as small theropods, armored ankylosaurs, and giant plant-eating sauropods have been discovered, showing that the land was not empty, but was home to a wide variety of species. What makes these discoveries so interesting is that many of them suggest survival on a land that was already drifting apart and sinking. It raises the possibility that, while other continents saw species vanish or transform, Zealandia continued to nurture dinosaurs long after isolation. Think of Zealandia as a kind of island paradise, though one that was constantly changing. Islands in today's world often protect unusual and rare species. For example, Madagascar is famous for its lemurs, which are found nowhere else, while the Galapagos Islands shelter unique reptiles and birds. This happens because isolation prevents other animals from moving in and out freely. Over long stretches of time, the species that remain adapt in their own special ways, creating forms of life that cannot be found anywhere else. Zealandia may have played a similar role in the time of the dinosaurs. By cutting off populations from the rest of Gondwanaland, it may have allowed them to develop in different ways, possibly preserving older lineages that disappeared elsewhere. The very act of drifting away might have been a gift of survival. When Zealandia split, it took with it not just dinosaurs, but also plants and small creatures that formed the base of ecosystems. These ecosystems could continue with fewer disturbances than those on larger continents, where new species were constantly arriving and competing. Dinosaurs living on Zealandia may have had fewer rivals for food and fewer predators to fear. This combination of isolation and relative safety is what makes scientists think of Zealandia as a possible sanctuary. Of course, life was never simple or easy. Zealandia was sinking beneath the ocean as it drifted. Over tens of millions of years, much of it went underwater, leaving only mountain peaks and ridges above the waves. This shrinking landmass would have put pressure on the creatures living there. They had to adapt to smaller spaces, to new coastlines, and to ecosystems that were increasingly narrow. Some dinosaurs may not have survived these changes. Yet it is possible that others endured, clinging to these last ridges of land, just as some modern species cling to tiny islands today. The very survival of unique animals like the tuatara, a reptile that still lives in New Zealand and resembles ancient forms, shows how Zealandia could preserve life that vanished from elsewhere. There's also another possibility that adds wonder to the idea of Zealandia as a refuge. Some scientists suggest that certain lines of dinosaurs, particularly smaller bird-like ones, may have survived on Zealandia even after the Great Extinction event at the end of the Cretaceous period, around 66 million years ago. While most dinosaurs vanished, their descendants, the birds, carried on. Could Zealandia have given these early birds an advantage? Could its isolated forests and coasts have provided places where they were less exposed to global catastrophe? While there is no clear answer, the possibility deepens the mystery and makes Zealandia seem even more like a place where survival had a chance. It is important to think about what a refuge really means in the deep past. It does not mean a perfect paradise where every creature thrived without struggle. Instead, it means a land where certain species had just enough of what they needed to endure longer than they might have elsewhere. Maybe the forests of Zealandia provided steady food supplies with ferns, conifers, and flowering plants growing in abundance. Maybe its coastal seas offered rich sources of fish, supporting both marine reptiles and bird-like dinosaurs. Perhaps its mountainous ridges created pockets of cooler climate where creatures could escape heat or drought. All of these elements together could have formed the kind of balanced environment where survival was possible. When we imagine Zealandia in those ancient times, it is easy to picture dense forests with tall trees, rivers flowing into shallow seas, and dinosaurs moving through landscapes that combined mountains with wetlands. Large plant eaters may have grazed in open areas, while swift predators stalked them through ferns and undergrowth. Armored dinosaurs may have lumbered along riversides, protected by their plates and spikes. Overhead, flying reptiles and early birds wheeled through the sky. Beneath the waves, marine reptiles like mosasaurs and plesiosaurs swam, hunting fish and squid. In such a place, cut off from the rest of the world, life could continue on its own terms for millions of years. What makes this idea especially captivating is that Zealandia remained hidden from human knowledge for so long. Only in recent decades have scientists confirmed its existence as a true continent. For most of history, it was simply seen as scattered islands in the Pacific. The realization that it is a vast continent, mostly beneath the waves, changes how we see the past. It means that there was a whole stage for life's drama that was overlooked, a platform where dinosaurs and other creatures lived out stories we're only beginning to piece together. And within that hidden stage, the idea of refuge becomes even stronger. It was a secret sanctuary, unknown for so long, yet vital to the survival of ancient life. The very survival of unique modern species in New Zealand hints at this long history of refuge. The tuatara, mentioned before, belongs to a reptile order that flourished alongside dinosaurs, but disappeared everywhere else. Its survival in New Zealand shows that isolation can protect even fragile lineages for astonishing lengths of time. Similarly, New Zealand's flightless birds, such as the kiwi, may trace part of their heritage back to ancient birds that shared the land with dinosaurs. These living examples strengthen the case that Zealandia has always been a place where life, cut off from the rest of the world, has managed to preserve what was lost elsewhere. Thinking about Zealandia as a refuge also helps us understand how survival and extinction work on a global scale. Species do not simply vanish everywhere at once. Often they retreat into safe corners, holding on in hidden places long after disappearing from the mainlands. These refugees are like time capsules, preserving forms of life until conditions finally overwhelm them. Zealandia, by breaking away and becoming isolated, created one of the largest natural refugees Earth has ever seen. It is not hard to imagine that some dinosaurs managed to live there longer than their cousins elsewhere, hidden away while the rest of the world changed around them. Even if no dinosaurs survived the final extinction there, the fact that they lived on Zealandia for so long shows how powerful isolation can be. It reminds us that survival often depends on being in the right place at the right time. For countless generations of dinosaurs, that place may well have been Zealandia. And even after the age of dinosaurs ended, the same land went on to shelter other unique life forms, continuing its role as a safe harbor across deep time. The earliest discoveries that hinted at dinosaurs in the faraway land of New Zealand and the much larger submerged continent of Zealandia are not the kind of moments that came suddenly with trumpet-like announcement. They were quiet, almost accidental, and often began with curious rocks being picked up by hands that did not fully realize what secrets they carried. These secrets were locked away for tens of millions of years, hidden in stone, waiting for the right eyes to notice them. What makes these discoveries fascinating is not only the fossils themselves, but also the slow journey of realization, the way fragments of bones, teeth, and imprints began to reshape ideas about what kind of animals once roamed these lands. that now covered in thick forests, mountains, valleys, and in the case of Zealandia, a world mostly submerged under the sea. The first fossil finds in New Zealand that were linked to dinosaurs were discovered in the 19th century, at a time when the science of paleontology itself was still very young. The very word dinosaur had only been created in the year 1842 by Richard Owen, a British scientist who wanted to describe a group of giant reptiles that were unlike anything alive in his own time. News of dinosaur fossils in Europe and North America captured the imagination of scholars and ordinary people. But the idea that such creatures might also have lived in the remote islands of the South Pacific was not something many considered. New Zealand had only recently been colonized by Europeans in the 19th century, and scientific exploration was just beginning to spread across its landscapes. One of the earliest discoveries came in the 1800s, when fossilized bones and fragments were unearthed in coastal cliffs and riverbanks. At first, these bones were puzzling. Some of them were mistaken for the remains of large birds, which is understandable given that New Zealand is the land of giant birds like the moa, a flightless bird that stood taller than a man and lived until only a few hundred years ago. The moa had already amazed settlers and scientists with its massive skeletons, and so when strange fossils were found, the immediate thought was that they belonged to birds. Only later did careful examination reveal that some of these bones were far older and belonged to reptiles that had lived during the age of dinosaurs. In the year 1861, a discovery was made near Hawke's Bay on the eastern coast of New Zealand, North Island. Fossil bones were found that looked very different from bird bones, and they stirred excitement among scientists. They were preserved in ancient rocks that dated back to the Cretaceous period, more than 70 million years ago. This meant that dinosaurs had indeed walked on the land that would one day become New Zealand. These bones were fragmentary, and they did not form a complete skeleton, but they carried enough clues in their shape and structure to tell scientists that they belonged to creatures that were part of the dinosaur family. For the first time, the possibility that New Zealand had once been home to dinosaurs was becoming real. Other finds followed in later years, often discovered by farmers, quarry workers, or explorers who noticed unusual shapes in rocks. Sometimes children stumbled across strange-looking bones or teeth while playing along riverbeds or coastal areas. The land itself seemed to hold traces of a forgotten time, and every fragment that was unearthed added a new piece to the puzzle. These discoveries were never as numerous as those in places like North America or Mongolia, where entire dinosaur skeletons were found, but they were enough to show that dinosaurs had been present in Zealandia. What made these finds special was not their size or completeness, but the way they opened a window into a world that had long vanished. Scientists studying these fossils often faced challenges. Many of the bones were incomplete, broken, or worn down by the passage of millions of years. Some were so small or fragile that it was difficult to identify exactly what kind of dinosaur they came from. But with patience, skill, and comparisons to other fossils found around the world, researchers began to piece together the picture. They identified evidence of both plant-eating dinosaurs and meat-eating dinosaurs. Among the remains were those of theropods, the group of dinosaurs that includes the famous Tyrannosaurus rex and the ancestors of modern birds. There were also bones that belonged to long-necked plant-eaters and possibly to duck-billed dinosaurs. Each discovery, no matter how small, told a story of life in a land that was once part of the great supercontinent of Gondwanaland. The wider continent of Zealandia, of which New Zealand is only the highest part still above water, was once connected to Gondwanaland before breaking away around 85 million years ago. Back then, Zealandia was not a scattered collection of islands, but a much larger landmass covered with forests, rivers, and habitats where dinosaurs could thrive. The fossils found in New Zealand are not only clues to the creatures themselves, but also to the shape and history of Zealandia. They show that this sunken continent, though mostly hidden beneath the waves today, was once alive with animals that were part of the global story of dinosaurs. In the year 1874, more discoveries were made in the Waipara River area of the South Island. Fossilized bones and vertebrae were unearthed, and they puzzled scientists for years. Some of these belonged to marine reptiles like plesiosaurs and mosasaurs, which were not dinosaurs, but lived alongside them in the oceans. These creatures were fierce predators of the seas, with long jaws filled with sharp teeth. Their fossils reminded people that Zealandia was not just a land of forests, but also surrounded by rich seas where giant reptiles hunted. The mixing of dinosaur fossils with those of marine reptiles painted a vivid picture of life, both on land and in water. In the 20th century, fossil hunting in New Zealand became more systematic. Geologists and paleontologists began exploring areas where Cretaceous rocks were exposed, knowing that these rocks had the best chance of preserving remains from the age of dinosaurs. In the 1920s and 1930s, more fossil bones were found that confirmed the presence of both large and small dinosaurs. Each find was celebrated, and each one added more credibility to the growing idea that Zealandia had once been a true home for these ancient creatures. By the 1970s and 1980s, discoveries in places like Mangahuanga Stream in Hawke's Bay revealed more fascinating fossils. This stream became one of the most important fossil sites in New Zealand. In its gravel beds, scientists uncovered bones of small theropods, long-necked sauropods, and marine reptiles. These finds were exciting because they were relatively well-preserved compared to earlier fragments. The Mangahuanga fossils gave a clearer glimpse into the variety of dinosaurs that once lived in Zealandia. Among the discoveries were bones that suggested the presence of hypsilophodonts, small plant eaters that could move quickly on two legs. There were also teeth and bones from larger predators, showing that the ecosystem had both hunters and prey. One of the most remarkable aspects of these discoveries is the way they connected New Zealand to other parts of the ancient world. Many of the fossils resembled dinosaurs found in Antarctica, Australia, and South America, all of which were once connected through Gondwanaland. This suggested that dinosaurs were able to move across vast distances when the continents were joined, spreading into Zealandia before it drifted away and became more isolated. The fossils thus became evidence not only of the animals themselves, but also of the great geological movements that shaped the Earth. As time went on, more modern technology helped scientists study these fossils in detail. High-powered microscopes, scanning machines, and comparisons with vast fossil collections from other countries gave clearer pictures of what these dinosaurs looked like and how they lived. For instance, some of the theropod fossils showed traits linking them to the group of dinosaurs that eventually evolved into birds. This was especially fascinating in New Zealand, a land famous for its unusual bird life. The idea that the ancestors of birds might have lived there millions of years earlier created a sense of continuity between the ancient world and the present. Children in schools across New Zealand began to learn about these discoveries, and museums displayed the fossils with pride. Though the skeletons were never as complete as those found in other lands, the excitement of knowing that dinosaurs had walked and lived in Zealandia inspired generations. Each discovery was like a whispered reminder from deep time, telling of a world that once was, a world now hidden beneath forests and seas. The search for fossils continues even today. Paleontologists return to streams, cliffs, and quarries, sometimes finding new fragments that had been overlooked before. They know that the story is far from complete, and every piece of bone or tooth might belong to a species that has never been identified. Some fossils still lie buried, waiting for storms, floods, or human curiosity to bring them into the light. The work is slow, but the rewards are immense, for each fossil holds the power to change how we see the past. What makes the early discoveries so powerful is the way they began with uncertainty. A fragment of bone mistaken for a bird, a tooth thought to belong to some unknown fish, a vertebra puzzled over by generations. All of these were small steps toward the realization that dinosaurs once lived in New Zealand. The fragments were like scattered words of a forgotten language, and it took time and patience for scientists to begin to read them. Yet, with each new find, the language of the fossils became clearer, and the picture of Zealandia as a land of dinosaurs grew more vivid. The early fossil finds of dinosaurs in New Zealand and Zealandia were more than just scientific curiosities. They were treasures that connected the present to a distant past, reminding us that the land beneath the feet of modern people once carried giants and strange creatures. They were pieces of a puzzle too big for any single person to complete. But together, they show that even in the most remote corners of the world, the age of dinosaurs had left its mark. When trying to imagine the early fossil discoveries in New Zealand and Zealandia, it helps to place ourselves in the shoes of those first finders. Picture a settler farmer in the mid-19th century walking along a stony riverbank after a heavy rain. The swollen waters of the river had washed away part of the bank, revealing fresh layers of rock that had not been seen for ages. Among the scattered stones and driftwood, something unusual catches the eye, perhaps a bone-like fragment sticking out of the mud, harder and heavier than normal bone. The farmer picks it up, puzzled, and perhaps assumes it belonged to a cow or a sheep, not realizing that what rests in his hands is many millions of years old. Such moments happened more often than we know, because in those days, few people had the training to recognize fossils for what they truly were. The land itself often served as the real discoverer. Earthquakes shook cliffs, landslides tumbled rocks, and floods carried fragments downstream. In this way, fossils that had been buried deep for tens of millions of years were suddenly brought to light. Local children playing in the shallows sometimes stumbled upon the strange stone-like shapes that looked like no ordinary bone. The excitement of these accidental finds was part of the charm of fossil hunting in New Zealand. It was not a land of grand digs with teams of scientists and vast skeletons being unearthed in deserts as in the United States, but a land of quiet, modest discoveries where a single bone fragment could make all the difference. The Mangahuanga stream discovery in Hawke's Bay is an excellent example of this. In the 1970s, Joan Whiffen, a self-taught paleontologist, began exploring this remote stream bed. She had no formal training in paleontology, yet her determination and passion led her to uncover some of the most important dinosaur fossils ever found in New Zealand. She would walk the rocky stream bed, carefully picking through gravel and sediment, searching for tiny signs that others might miss. It was painstaking work, but her keen eye soon paid off. She found bones that clearly did not belong to fish, birds, or modern reptiles. Among them were vertebrae, limb bones, and teeth that pointed to theropods, sauropods, and even ankylosaurs. Each fossil was like a small window into the Cretaceous world of Zealandia. The fact that a woman without formal scientific credentials made such groundbreaking discoveries is a story in itself. It shows how fossil hunting in New Zealand was often about persistence, curiosity, and love of discovery, more than about grand institutions or well-funded expeditions. Joan Whiffen's fossils proved beyond doubt that dinosaurs had once walked on Zealandia, and her work inspired both professional scientists and ordinary people. Without her dedication, much of what we now know about New Zealand's dinosaurs would still be hidden beneath stone. One remarkable aspect of the fossils found in Zealandia is the range of creatures they represent. In addition to theropods, which were agile hunters walking on two legs, there were bones from long-necked sauropods. These were massive plant eaters, their necks stretching to reach leaves high in the trees. To imagine such a creature moving through what is now a quiet valley or forest in New Zealand gives a sense of how different the land once was. Fossils also revealed the presence of armored dinosaurs like ankylosaurs, covered with bony plates and spikes that protected them from predators. This suggests that Zealandia hosted a surprisingly diverse range of dinosaurs, even if the fossils are fragmentary. The marine reptiles found in the Waipara River added another layer to the story. Plesiosaurs, with their long necks and paddle-like limbs, glided through the waters that once surrounded Zealandia. Mosasaurs, powerful predators with jaws filled with sharp teeth, hunted fish and smaller reptiles. These creatures were not dinosaurs, but they lived at the same time and often dominated the fossil record of New Zealand. The Waipara fossils include teeth and bones that speak of fierce battles and a dangerous life in the ancient seas. When people first discovered these fossils in the 19th century, they were astonished by the size of the bones and teeth. Some teeth were longer than a human finger, sharp and curved, leaving little doubt that the creature that once owned them had been a fearsome predator. The early years of fossil discovery in New Zealand were filled with both excitement and confusion. Scientists tried to compare the bones to those found in Europe and North America, but many fossils were incomplete or broken. Sometimes misidentifications occurred. A bone might be labeled as belonging to a bird, a reptile, or even a mammal before later study revealed its true identity. This uncertainty shows how difficult it was to study fossils in a land so far from the great centers of science in the 19th and early 20th centuries. Communication with scientists overseas was slow, and access to large collections for comparison was limited. Still, little by little, the picture grew clearer. The geology of New Zealand and Zealandia added further complications. Much of the continent lies beneath the ocean, and only small portions are exposed on land. Fossils are relatively rare, and those that do exist are often locked in hard rock or scattered in riverbeds. Unlike in North America, where entire dinosaur graveyards have been found, New Zealand offered only fragments here and there. This made every discovery precious. A single bone from Mangahuanga stream could represent the only known evidence of that particular species in the entire country. That sense of rarity made fossil hunting both challenging and thrilling. When considering the age of these fossils, one must remember that the rocks of New Zealand hold records from the Cretaceous period, between about 145 million and 66 million years ago. During this time, Zealandia was still connected to Gondwanaland and later drifted away, becoming more isolated. This isolation may have shaped the kinds of dinosaurs that lived there. Scientists believe that some dinosaurs in Zealandia might have evolved unique features because of their separation from other populations. Unfortunately, the fragmentary fossils make it hard to say for sure, but the possibility lingers, sparking the imagination. Imagine standing in New Zealand during the Cretaceous. The land was warmer, covered with conifer forests, ferns, and flowering plants that were spreading across the world at that time. Rivers wound through valleys, and coastlines stretched far wider than today. In these forests, small plant-eaters like hypsilophodonts darted on two legs, feeding on low vegetation. Large sauropods moved slowly, their long tails swinging as they reached for leaves. Predatory theropods hunted among them, their sharp teeth and claws making them fearsome threats. Overhead, early birds flapped through the air, while in the seas around Zealandia, plesiosaurs and mosasaurs lurked beneath the waves. It was a world full of life, very different from the islands of today. The early fossil discoveries were also deeply influenced by the cultural and natural history of New Zealand. For the Maori people, the indigenous people of the land, bones found in the earth were sometimes interpreted as the remains of ancestors or of legendary creatures. Giant bird bones, for example, were linked to the moa and carried cultural meaning. When European scientists began to describe dinosaur fossils, these interpretations created moments of cross-cultural encounter. The fossils became symbols of both ancient natural history and the living traditions of the land's people. Though the European scientific perspective dominated the written records, the Maori sense of deep connection to the land added another layer of meaning to these discoveries. In the 20th and 21st centuries, the study of Zealandia's fossils continued to expand. Scientists began to understand that the continent, though mostly underwater, was large enough to have supported a wide range of ecosystems. Fossils from various sites revealed not just dinosaurs and marine reptiles, but also ancient turtles, fish, and even early mammals. The dinosaur fossils remained rare, but their very rarity made them valuable. When a new bone or tooth was discovered, it often became headline news in New Zealand. Children visiting museums could see these fragments on display, imagining the giants that once walked their homeland. Another important aspect of the early discoveries is the way they connected New Zealand to Antarctica. Fossils found in both places showed striking similarities, suggesting that dinosaurs once moved freely between them when both were part of Gondwana land. This was long before Antarctica was covered in ice, at a time when forests grew there and dinosaurs thrived in its milder climate. The connections across continents emphasized that Zealandia was part of a much larger story, one that stretched across the southern hemisphere. Each fragment of bone was not just evidence of a single animal, but a piece of a global puzzle. Even today, the work of identifying fossils in New Zealand is not finished. Many old discoveries are being re-examined with new technology. Fossils that were once labeled uncertain are scanned with powerful machines, revealing tiny details of their structure. These details sometimes change old assumptions. A bone once thought to belong to one kind of dinosaur may turn out to belong to another. Teeth may show new information about diets and behavior. The process of discovery is ongoing, and each re-examination is a continuation of those first moments when a puzzled settler, scientist, or child picked up an unusual stone and wondered what it might be. The earliest discoveries of dinosaur fossils in New Zealand and Zealandia were not grand in scale, but they were immense in their significance. They began with small fragments, uncertain interpretations, and patient study. Over time, they revealed that even this distant and isolated part of the world had once been alive with dinosaurs. They reminded people that the ground beneath their feet carried a memory of deep time, a memory written in stone and bone, and they opened the imagination to the possibility of countless other secrets still waiting to be found, hidden in the rocks and rivers of a land where history stretches back far beyond human memory. Moa and dinosaurs may seem like two completely different creatures, one belonging to the deep prehistoric past and the other walking the land of New Zealand until only a few hundred years ago. But they are tied together in a way that stretches across tens of millions of years. To understand how giant flightless birds, such as the moa, connect to the ancient story of dinosaurs, one must look closely at the history of evolution, the strange pathways life has taken, and the land that sheltered creatures long after others had disappeared. Dinosaurs, as people often imagine them, were massive reptiles that roamed the world during the Mesozoic era, a time that lasted for about 180 million years. Yet the truth is that not all dinosaurs vanished at the end of that age, when a massive impact struck Earth and sent clouds of ash into the skies. One branch of dinosaurs, the one we now call birds, survived and kept evolving. Over time, these survivors spread, changed, and adapted, and in some remote places they grew into giants again, echoing the shapes and behaviors of the dinosaurs that came before them. Moa was part of that story. The moa were birds unlike anything alive today. They could not fly. They had long legs, powerful bodies, and they grew taller than almost any bird that ever lived. Some species of moa stood as tall as 3 meters, towering above the heads of humans. They lived only in New Zealand, a land that had drifted apart from the great supercontinent of Gondwanaland around 85 million years ago. That separation made the land a kind of floating sanctuary, where mammals were rare and where birds, reptiles, and insects became the rulers of the wild. On that isolated stage, evolution could take dramatic turns, and the moa filled ecological spaces that in other lands were occupied by large plant-eating mammals. They browsed on leaves, twigs, and fruits, walking slowly through forests and grasslands, feeding much like deer or cattle do elsewhere, yet doing so without any mammalian competition. When people talk about dinosaurs and birds being related, it is sometimes hard to picture because birds look so small and fragile compared to the giant reptiles of the past. But fossil evidence has shown again and again that birds are not just distant cousins of dinosaurs. They are living dinosaurs themselves. Many dinosaurs, especially the group called theropods, had feathers, hollow bones, and other features we see in birds today. Velociraptor, for example, is more bird-like than reptile when studied closely. The lineage that gave rise to birds survived when the asteroid ended the reign of the other dinosaurs about 66 million years ago. Those early birds evolved into countless forms, spreading across the world. Some becoming small songbirds, others becoming seabirds. And in certain places like New Zealand, some becoming large and flightless, filling the role of the ancient giants that once thundered across the land. The moa belonged to that surviving branch, and in their giant size and way of life, they seem like echoes of the lost world of dinosaurs. Life on islands often creates creatures that are unusual. With no large predators around, birds can safely give up flight, and with abundant food, they can grow much larger than their ancestors. That is what happened in New Zealand. Because there were no lions, no tigers, no wolves, and no large mammals of any kind, the moa thrived and grew. Their wings became smaller until they disappeared altogether. Unlike ostriches and emus, which still keep small wings even though they do not fly, the moa lost their wings completely. This made them unique among birds. They walked on strong legs, stood tall like towers in the forest, and used their long necks to reach leaves high above. It is easy to imagine them moving slowly in groups, their necks swaying like the long-necked sauropod dinosaurs of ancient times. Creatures like Brachiosaurus or Apatosaurus, though of course much smaller in size. Still, their presence carried a shadow of that older time when reptilian giants ruled the world. The connection between moa and dinosaurs is not only in appearance or size, but in ancestry. Moa were part of the group of birds called ratites, which also includes ostriches in Africa, emus and cassowaries in Australia, and rheas in South America. All of these share a distant ancestor that was already present when the great southern supercontinent Gondwanaland still existed. When Gondwanaland broke apart into pieces, these bird lineages became isolated on different continents. Over time, they evolved separately, and in New Zealand, the moa lineage had no land mammals to compete with, so they could expand into many species. Scientists believe there were at least 9 different kinds of moa, ranging from smaller turkey-sized ones to the giants that stood taller than any human. This variety shows how deeply they had become part of the ecosystem, occupying nearly every type of environment, from mountain slopes to dense forests. To people who lived alongside them, especially the first Polynesian settlers who arrived in New Zealand around the 13th century, moa were creatures of both wonder and food. These giant birds provided meat, feathers, and bones that could be shaped into tools. For humans, encountering such a large and unusual bird must have been both awe-inspiring and practical. But it also led to the moa's disappearance. For hunting, combined with the burning of forests and the changing of the land, drove them to extinction within only a few hundred years. By the 15th century, Moa had vanished completely, leaving behind only their bones, eggshells, and the memories preserved in oral traditions. In a way, this was a second extinction of giants, a smaller mirror of what had happened millions of years earlier when the asteroid had ended the age of dinosaurs. The Moa's link to dinosaurs becomes clearer when fossils are compared. Scientists studying the bone structures of Moa have noticed many features similar to their distant theropod ancestors. Their pelvis, their legs, and even the way their muscles attach to bones connect them to that older story. When fossils of feathered dinosaurs were found in China, the picture became even sharper. Those creatures looked very much like oversized birds that simply had not taken flight. By piecing together such evidence, scientists can trace a line from dinosaurs like Velociraptor and Troodon through early primitive birds like Archaeopteryx, all the way to the moa that walked New Zealand's forests. The loss of flight in Moa is also part of that story of connection. Many dinosaurs, even those that were not flyers, had feathers or feather-like structures. Some used them for warmth, some for display, and some possibly for gliding. The earliest birds used feathers for flight, but when some of their descendants reached New Zealand and found a land with no predators, flying became unnecessary. Over thousands of years, wings shrank and vanished. It is as if the evolutionary experiment of flight reversed itself, leading back to a form that resembled the grounded dinosaurs of old. In that sense, the moa's body became an echo of its deeper ancestors. One cannot ignore the strange feeling of time overlapping when imagining moa as living dinosaurs. The asteroid impact that marked the end of the Cretaceous happened 66 million years ago. Yet in New Zealand, humans lived side by side with birds that were direct descendants of those survivors. People could see with their own eyes a creature that carried within its body the history of dinosaurs. The fact that Moa lived into such recent times reminds us that the dinosaur story did not end in distant ages, but continued into the age of people. The connection between Moa and dinosaurs is not simply about shared bones or features, but about the long persistence of life, the survival of one lineage that could adapt to new worlds and new ages. The land of New Zealand itself added to this connection. Zealandia, the sunken continent to which New Zealand belongs, had split from Gondwanaland long before the asteroid impact. This meant that when dinosaurs still roamed the Earth, Zealandia was already drifting away into the Pacific. Some believe that primitive relatives of Moa may have already been present on that land, carried away like passengers on a drifting raft of continent. If so, then Moa were part of a living chain that stretched directly from the age of dinosaurs into the age of humans. Their presence in New Zealand was not just chance, but the result of deep geological history. In the imagination, Moa can be seen as modern-day analogues of plant-eating dinosaurs. Just as sauropods used their long necks to strip leaves from trees, Moa stretched upward to feed on foliage. Just as herds of herbivorous dinosaurs shaped their landscapes, Moa herds may have shaped New Zealand's forests and grasslands. Their feeding patterns likely influenced which plants thrived and which did not, creating a rhythm between vegetation and giant birds that mirrored the balance that once existed between plants and dinosaurs. Without large mammals, the ecological role of shaping the land fell upon these giant birds, making them not only connected to dinosaurs by ancestry, but also by function. The study of Moa bones has revealed fascinating details. Some bones still contain traces of DNA, allowing scientists to study their genetics and understand their evolutionary place among birds. By comparing that DNA to modern species, researchers can map how Moa fit into the larger bird family tree, showing clearly that they share a branch with other ratites and ultimately link back to dinosaur roots. This genetic evidence adds another layer of connection, proving not only by shape, but also by molecular signature that moa were living dinosaurs in their own right. Legends and oral traditions of the Maori people also preserved echoes of moa. Stories tell of enormous birds that roamed the forests, creatures so large that they could not be taken down easily. These tales may have been inspired by real encounters with moa, memories passed down through generations even after the birds themselves were gone. In this way, moa became not just biological connections to dinosaurs, but also cultural bridges, linking human imagination with the primeval past. They stood as reminders that Earth had once been filled with giants, and that some of those giants had walked among people. The way moa moved, fed, and lived continues to be reconstructed by scientists. By examining the wear on their beaks, the shape of their bones, and the spaces where muscles once attached, paleontologists can imagine how they grazed and browsed, how they ran across open fields, and how they raised their young. In these reconstructions, moa appear as creatures both bird-like and dinosaur-like, carrying with them the echo of two different times. To see a moa skeleton in a museum today is to glimpse a creature that bridges two worlds, a world of feathered dinosaurs and a world of human hunters. The extinction of moa also connects back to the extinction of dinosaurs. Both were caused not only by natural changes, but also by sudden, overwhelming forces. For the dinosaurs, it was the impact of a giant asteroid and the environmental collapse that followed. For the moa, it was the arrival of humans and the pressures of hunting and habitat destruction. In both cases, creatures that had thrived for millions of years disappeared in what felt like a blink of an eye in geological time. The parallel is striking, making the moa's story feel like a smaller reflection of the larger dinosaur saga. Moa also reminds us how fragile survival can be. Their ancestors had lived through the most catastrophic event in Earth's history, the asteroid strike that killed the dinosaurs, yet they could not survive the relatively small-scale changes brought by human arrival. In that way, the connection between moa and dinosaurs is also one of fate and vulnerability. Both were giants in their own right, and both vanished when the balance of their world shifted too quickly. Imagining moa alive today is like imagining dinosaurs alive again. Their size, their strange shapes, their ancient lineage would have given people a direct glimpse into the deep past. Some explorers and settlers in the early years of New Zealand ES colonization even wondered if giant birds might still be hidden in remote valleys. Although none were ever found, the idea speaks to how deeply the presence of moa stirred the imagination, much as dinosaur fossils stir wonder today. The scientific study of moa continues to reveal details about their life cycle, their growth, and their diversity. Some moa species laid eggs that were among the largest of any bird, massive oval shells that could have held enough food to feed a family. The moa, as much as they were extraordinary in their size and presence, also had behaviors that connected them in fascinating ways to their distant dinosaur ancestors. Their daily lives, their feeding, their breeding, and even the way they shaped their landscapes all reveal echoes of the patterns that had existed millions of years before in the age of the dinosaurs. By looking closely at their behavior, at the fossil remains they left behind, and by comparing them with their ratite relatives, one can begin to see how these birds were living windows into the ancient past. Moa were plant-eaters, and their feeding habits were as diverse as the many species that existed. Some moa had short, strong beaks, which they used for browsing tougher plants, snapping twigs, and stripping leaves from shrubs. Others had more delicate beaks, suited for nibbling softer leaves and fruits. Studies of fossilized gizzard stones, which are small pebbles swallowed by birds to help grind up food, have shown that moa used this same technique, just as many dinosaurs once did. In sauropod dinosaurs like Apatosaurus or Diplodocus, gizzard stones helped them digest the vast quantities of plant matter they consumed. In Moa, the same method was preserved, connecting a bird of recent history to a reptilian giant of deep time through the shared behavior of swallowing stones to aid digestion. This simple act links two worlds separated by millions of years. Their movement across the land also played an important role. Large herds of moa may have moved through forests and open plains, creating paths and affecting vegetation. By trampling certain areas and grazing heavily in others, they influenced which plants survived and spread. This is very similar to the way herds of plant-eating dinosaurs shaped their environments. The long-necked sauropods of the Jurassic, with their endless appetite for leaves, transformed their forests. Likewise, moa in New Zealand helped control the growth of certain plants and allowed others to flourish, creating a kind of living balance between giant bird and forest. In this way, they were not just inhabitants of the land, but architects of it, much as dinosaurs had been. When it comes to fossil discoveries, moa left behind an unusually rich legacy. Unlike dinosaurs, which disappeared tens of millions of years ago, moa only vanished several centuries ago. This means that their bones are often found in excellent condition, sometimes with skin, feathers, or soft tissues still preserved in dry caves and peat bogs. These remains have given scientists an incredibly detailed look at how moa lived and what they looked like. For example, feathers found in caves showed that moa plumage was brownish, with a hint of reddish or yellow patterns, colors that may have helped them blend into the forests of New Zealand. Eggshell fragments have also been uncovered, some of them enormous, showing just how large moa eggs were. The biggest moa eggs were more than 24 centimeters long, rivaling the size of ostrich eggs, but more elongated and strong enough to hold developing chicks that would one day grow into towering adults. The richness of moa fossils even extends to DNA. In some bones, enough genetic material has survived for scientists to sequence parts of the moa genome. This has allowed researchers to study their family relationships, their diversity, and even the possibility of recreating aspects of their biology. The study of ancient DNA has revealed that there were at least 9 species of moa, each adapted to different environments, from mountain slopes to swampy lands. It has also shown how they were related to other ratites, such as emus and ostriches, and how they fit into the larger story of bird evolution. Comparisons to other ratites help highlight just how unusual moa were. Ostriches, for example, are the largest living birds today, but they still have small wings that they use for balance and display. Emus and cassowaries also retain small wings and have powerful legs for running and defense. Moa, however, had no wings at all, not even small ones. Their skeletons show no traces of wing bones, making them the only birds known to have completely lost their wings. This sets them apart even from their closest relatives. In this sense, moa had taken the path of flightlessness further than any other bird, turning themselves entirely into ground dwellers. It is almost as if they had stepped away from the bird world and back into the shape of the grounded dinosaurs that came before them. The way moa nested and raised their young also carries connections to dinosaurs. Fossilized eggs and eggshells suggest that moa laid fewer eggs than many birds, but each egg was enormous, investing much energy into each chick. This is similar to some dinosaurs, which also laid large eggs and invested heavily in their offspring. In certain nesting sites of hadrosaurs and oviraptors, scientists have found fossilized eggs arranged carefully in nests, showing that dinosaurs took great care with their young. While direct evidence for moa parenting is limited, it is reasonable to think that they, too, invested care into raising chicks, given the size of their eggs and the slow-growing nature of such large birds. In this way, behavior crossed the boundaries of millions of years, linking birds and dinosaurs through the shared duty of parenthood. The comparison between moa and dinosaurs becomes even clearer when looking at anatomy. Moa legs were thick and strong, built for supporting heavy bodies and walking long distances. Their pelvises had a structure similar to that of theropod dinosaurs, reflecting their shared ancestry. Their long necks allowed them to reach vegetation, much like sauropods had done. Even their skulls, though bird-like, carried echoes of dinosaur structure, with certain features in the bones resembling those of their ancient reptilian cousins. In terms of diversity, moa matched the variety seen in dinosaurs, though on a smaller scale. Some moa species were tall and slender, adapted to reaching high leaves. Others were shorter and sturdier, adapted to grazing lower vegetation. This mirrors the way dinosaurs came in countless shapes. Some adapted for speed, others for strength, and others for browsing at different heights. New Zealand's isolation allowed moa to fill almost every plant-eating role, much like dinosaurs had once done across the continents of the world. The discovery of moa fossils has been an ongoing story for more than 2 centuries. In the early 19th century, European settlers in New Zealand began finding strange bones in riverbeds and caves. At first, these bones puzzled scientists, who struggled to understand what kind of creature they belonged to. Some thought they were from a kind of giant eagle or other bird, while others speculated they were from long-lost mammals. It was only after careful study by naturalists, such as Richard Owen in the 1840s, that the truth became clear. These were the bones of enormous flightless birds. Owen, who would later coin the term dinosaur, helped bring moa to the attention of the scientific world, linking them indirectly to the growing discoveries of fossil reptiles elsewhere. As more moa bones were uncovered, sometimes in huge numbers, it became clear that these birds had once been widespread and abundant. Cave systems in Otago and Canterbury yielded skeletons preserved in astonishing condition. Swamps and bogs also offered up remains, sometimes with soft tissue still intact. These finds gave scientists a rare chance to study not just the hard skeleton, but also the outer coverings of feathers and skin, something almost never possible with dinosaurs. The level of preservation made moa one of the best documented examples of an extinct giant bird, allowing researchers to compare them in detail to both modern birds and ancient dinosaurs. The link between moa and dinosaurs deepened with the discoveries of feathered dinosaurs in the late 20th and early 21st centuries. Fossils from China showed theropods covered in feathers, with wings and tails that looked strikingly bird-like. Some of these dinosaurs were nearly indistinguishable from primitive birds. This blurred the line between what was called dinosaur and what was called bird. Moa, though much more recent, stood as proof that the line truly had never been broken. Birds were not only descendants of dinosaurs, they were dinosaurs themselves, living on into the present. The moa's giant size and dinosaur-like form made this truth all the more visible. Moa also provides an example of how evolution can circle back on itself. The earliest birds gained flight as an advantage, escaping predators and finding new food sources. Yet, in New Zealand, where there were no large mammalian predators, flight was no longer necessary. Over thousands of years, the moa's ancestors gradually lost their ability to fly, growing larger and more grounded. In doing so, they became once again similar to their dinosaur ancestors, as though time had turned backward. The arc of evolution had carried them from grounded reptilian dinosaurs to flying birds, and then back again to grounded bird giants. The story of moa and dinosaurs also has a human side. When Polynesian settlers first arrived in New Zealand, they encountered a land of strange and unique creatures. Among them, the moa must have seemed almost mythical in their size and presence. Imagine walking into a forest and encountering a bird taller than yourself, with a long neck rising into the trees and massive legs that could run with surprising speed. For early people, these birds would have been both a source of awe and a source of food. Hunting moa became an important activity, and their remains in ancient cooking sites show how deeply they were woven into human life. But the pressure of hunting, along with habitat destruction, quickly overwhelmed the moa, and within only 2 or 3 centuries, they were gone. This rapid extinction mirrors the sudden disappearance of dinosaurs 66 million years earlier, though on a smaller scale. Moa fossils have also inspired myths and stories. Maori traditions speak of giant birds that lived in the forests, sometimes feared, sometimes respected. Some of these stories may have been based on real encounters, while others may have been memories passed down after the moa were gone. These legends connect cultural memory with natural history, keeping alive the sense of wonder that such giant creatures inspired. In more recent times, moa have even been suggested as candidates for scientific resurrection through cloning or genetic engineering. Because DNA has been preserved in some moa bones, scientists have considered whether it might one day be possible to bring them back. While this remains only a dream for now, the very idea shows how strongly moa capture the imagination. Much like dinosaurs themselves do, the possibility of seeing a giant bird like a moa walk the land again stirs the same excitement as imagining a dinosaur reborn. When thinking of moa as part of the dinosaur story, it is important to see them not as separate chapters, but as a continuous line. Dinosaurs dominated the Earth for over 160 million years. At the end of that reign, one branch survived and kept evolving. That branch became birds, and among those birds, some grew into giants once again, living into the age of humans. The moa were the most striking of those giants, carrying within them the legacy of their dinosaur ancestors. Their bones, their behavior, and their disappearance all tie back to that larger story of life's rise and fall across time. The story of the moa becomes even richer and more striking when one looks closely at their ecology. The details of how they lived in their environment, how they interacted with the plants and landscapes of New Zealand, and how they resembled or differed from dinosaurs across the vast span of geological eras. The more one learns about the moa, the more they appear as bridges that connect the age of dinosaurs to the age of humans. They were not only birds of great size, but also engineers of ecosystems, shapers of forests, and living testaments to the survival of dinosaur lineages through time. The ecology of moa was wide-ranging because there were several different species, each adapted to particular environments. Some species lived in dense lowland forests, where their tall necks allowed them to pluck leaves from shrubs and trees. Others wandered in subalpine zones, grazing on tougher plants that could withstand cold and thin soils. In swampy regions, moa likely browsed on reeds and softer vegetation, their long legs allowing them to move easily through marshy ground. This division of ecological roles among species resembles the way dinosaurs once divided the environment among themselves. In the Jurassic and Cretaceous, there were small plant eaters that grazed close to the ground, mid-sized browsers that fed on shrubs, and towering sauropods that reached treetops. In New Zealand, moa species filled similar roles, from the small turkey-sized little bush moa to the giant South Island giant moa, which towered over 3 meters tall with its neck stretched. Each species contributed differently to the shaping of the landscape, creating a layered ecological system reminiscent of the age of dinosaurs. The feeding patterns of moa were not random, but showed clear adaptations. Their beaks were shaped in different ways depending on what they ate. Some had broad, strong beaks suited for tearing fibrous plants, while others had narrow, delicate beaks, better for nibbling soft leaves and fruits. The fossilized gizzard stones, also called gastroliths, give more detail. These stones, swallowed and stored in their muscular stomachs, helped grind tough plant material, just as some herbivorous dinosaurs did. The presence of these stones in Moa fossils is one of the clearest connections to their ancient relatives. Sauropods, for instance, also swallowed stones, and fossil sites have been found where clusters of smooth, rounded pebbles lie in the rib cages of giant skeletons. This parallel behavior, swallowing stones for digestion, links the Moa directly to creatures that lived more than 100 million years earlier. Moa also influenced the growth of forests and the spread of plants. Many native New Zealand plants evolved in the presence of Moa, and some developed features that seemed designed to withstand Moa browsing. Certain shrubs and small trees have divaricating branches, which are tangled and spread out in ways that make them difficult to eat. Scientists believe this may have been an adaptation to deter Moa, much like thorny plants evolved in Africa to discourage browsing by giraffes and antelope. When Moa went extinct, some of these plant defenses became unnecessary, and today they puzzle botanists until viewed in the context of Moa feeding. The plants still carry the marks of their ancient partnership with giant birds, much as the forests of the Mesozoic once bore the marks of dinosaur grazing. The Moa's role as ecological engineers mirrors the roles of dinosaurs across geological time. In the late Triassic period, the earliest dinosaurs were small, swift, and experimental in form. By the Jurassic, sauropods and stegosaurs shaped forests on a continental scale, their massive appetites changing plant communities. In the Cretaceous, hadrosaurs, ceratopsians, and ankylosaurs filled landscapes with herds that sculpted the vegetation. Moa, though far smaller and more recent, played a similar role in their island environment, showing how the same patterns can emerge in different times and places. The great herbivores of Earth, whether reptilian dinosaurs or avian Moa, left their mark on the very structure of the land. Fossil finds of Moa give remarkable windows into their lives. Unlike the fossils of dinosaurs, which are tens of millions of years old and usually preserved only as stone impressions or mineralized bones, Moa are often found in conditions that kept them surprisingly intact. In dry caves, Moa skeletons have been discovered with ligaments still holding bones together, feathers clinging to the skin, and even traces of muscle tissue preserved. In some cases, entire mummified remains have been found, showing the texture of the skin and the pattern of the feathers. These finds allow scientists to reconstruct the Moa's appearance with great accuracy, something nearly impossible with older dinosaurs, where paleontologists must sometimes guess at the colors of dinosaurs. Moa feathers provide direct evidence. In Otago and Canterbury, huge deposits of Moa bones have been found in swamps and riverbeds, sometimes in piles where birds became trapped in mud or quicksand. These sites suggest that Moa, like some dinosaurs, sometimes gathered in groups or herds. Imagine a flock of giant birds moving across a valley floor, their feet thudding against the ground, their long necks swaying as they browsed on plants. Such herds would have been a living echo of the dinosaur herds that once moved across the plains of Gondwana, and they left behind mass deposits of bones in much the same way. Human encounters with Moa add another layer of depth to their story. When Polynesian navigators arrived in New Zealand around the 13th century, they entered a land without mammals, but filled with birds. Among those birds were Moa, some towering as tall as a man, others even taller. For these first settlers, Moa were an astonishing resource. Huge birds that could provide vast amounts of meat. Archaeological sites show that Moa were hunted systematically, their bones split for marrow, their feathers used for clothing, and their eggshells used as containers. The size of Moa eggs meant that a single egg could feed a family. This intense use, combined with forest burning to clear land, quickly reduced Moa numbers. By the 15th century, only a couple of centuries after people first arrived, Moa were gone. This extinction was rapid and shocking, a human replay of the asteroid impact that had ended the dinosaurs. Both times, giant creatures that had dominated their environments vanished suddenly, leaving empty ecological roles behind. The Maori people remembered moa in their stories and traditions. Tales spoke of great birds in the forests, sometimes as prey, sometimes as fearsome beings. Some of these stories may have originated from real encounters, while others may have been passed down as memories after moa were gone. The oral traditions kept alive the knowledge that New Zealand had once been home to enormous birds, linking human memory with natural history. Just as ancient people across the world found dinosaur bones and wove them into myths of dragons and giants, Maori people kept the moa alive in stories long after the last one had died. Comparisons between moa and dinosaurs can stretch across all three major geological periods of the Mesozoic. In the Triassic, early theropods like Coelophysis were small, agile hunters with hollow bones and some features that foreshadowed birds. Moa, while plant eaters, still carried the hollow bones of their theropod ancestors. In the Jurassic, feathered theropods and early birds began to appear, blending the traits of reptiles and birds. Moa descended from this branch, carrying the lineage forward into the modern age. In the Cretaceous, some theropods were covered in elaborate feathers, some could fly, and others remained grounded but bird-like. The moa, appearing tens of millions of years later, stood as living reflections of those grounded, bird-like dinosaurs, their very bodies showing the survival of ancient traits. Even their extinction echoes dinosaur history. The asteroid impact 66 million years ago destroyed the ecosystems that sustained giant reptiles. The arrival of humans only a few hundred years ago destroyed the ecosystems that sustained giant birds. In both cases, creatures that had thrived for millions of years disappeared in the blink of an eye. The difference is that with moa, humans themselves were the asteroid, reshaping the land and ending an age of giants. The study of moa fossils continues to shed light on their behavior. Analysis of leg bones suggests that moa were not fast runners like ostriches, but steadier walkers, moving slowly but with endurance. This makes sense for a browsing herbivore with no natural predators. They did not need speed to escape, so they conserved energy, much like sauropods did in the Jurassic. Examination of eggshell thickness shows that moa eggs were surprisingly fragile, which may explain why they laid them in sheltered places. Dinosaur eggs, too, varied greatly in strength and size depending on species. Both moa and dinosaurs shared the challenge of protecting their young, and both adapted in different ways to that challenge. The possibility of bringing moa back through genetic science has been seriously discussed. Because moa DNA has survived in some bones, scientists have studied whether it might be possible to recreate moa through cloning or by inserting their genes into the eggs of living birds like ostriches. While such efforts are not yet close to reality, they show how strongly the idea of seeing a living moa excites the imagination. The thought of walking into a forest and encountering a giant bird again is as thrilling as imagining a dinosaur brought back to life. Moa, in this sense, remain symbols of the continuity of life across time, showing that the age of dinosaurs never truly ended, but lived on into modern history. The connection between moa and dinosaurs is, therefore, one of ecology, behavior, fossil record, and human imagination. They were giants of their world, like dinosaurs before them. They shaped their landscapes like dinosaurs before them. They vanished suddenly, like dinosaurs before them. And their bones, preserved in caves, swamps, and stories, remind us that the line between the ancient reptilian past and the recent human past is thinner than it first appears. To stand before a moa skeleton today is to look not only at a bird, but at a living thread of the dinosaur story stretched across millions of years and tied to the land of New Zealand. The world that existed tens of millions of years ago was unlike anything people can imagine today. And in the lands that later sank beneath the seas to form what scientists call Zealandia, there were creatures that left behind traces of their lives in rock and bone. Among the most fascinating of these creatures were the meat-eating dinosaurs, theropods, whose presence has been revealed through scattered and rare fossils found in New Zealand and the submerged parts of Zealandia. These theropods belong to the same great family of dinosaurs that included the famous Tyrannosaurus rex, the cunning velociraptor, and many other sharp-toothed hunters that once dominated the ancient world. Although the fossil record in this region is thin and broken compared to other continents, the clues that do exist suggest that Zealandia was once a place where terrifying predators prowled the forest's coastlines and plains, seeking prey in an ecosystem far removed from the islands we know today. The fossil record of New Zealand is challenging to piece together, because so much of Zealandia lies under the sea, and much of what once was land has been eroded or covered. Still, the bones and teeth that have been discovered tell a story that connects Zealandia with the wider world of the age of dinosaurs. In the late 20th century, researchers unearthed bones in places like Hawke's Bay on the North Island and in Otago on the South Island. These remains, while small in number, pointed strongly to the presence of meat-eating dinosaurs. Some of the bones showed the hallmarks of theropods, including the shapes of vertebrae and leg bones that matched known families of carnivorous dinosaurs found on other continents. These discoveries suggested that the theropods of Zealandia may have been related to large groups of predators that once roamed Gondwanaland, the ancient supercontinent that broke apart over 80 million years ago. When Zealandia split away from Gondwanaland, roughly 85 million years ago, it carried with it a sample of life from the ancient world. Among the plants and animals isolated on this drifting landmass were dinosaurs, both herbivores and carnivores, along with marine reptiles like plesiosaurs and mosasaurs in the surrounding seas. Over time, these creatures adapted to the changing landscapes and climates of Zealandia, some thriving for millions of years, while others dwindled. The theropods were especially important because they represented the top predators of their time, shaping the balance of life in their ecosystems. Evidence shows that Zealandia may have hosted a variety of theropods, from smaller, fast-moving hunters to larger, more powerful killers. The remains of theropods in Zealandia are often fragmentary, but paleontologists are skilled at reconstructing life from even the smallest of clues. A single tooth can reveal that a meat-eating dinosaur once bit into flesh in what is now New Zealand. Teeth belonging to theropods are usually sharp, serrated like knives, and curved for tearing meat, quite different from the flat, grinding teeth of plant eaters. Several such teeth have been found in New Zealand, showing that theropods did live there. One discovery involved teeth similar to those of the allosaur family, a group of large carnivores that were widespread across Gondwanaland. Another involved bones that bore resemblance to the coelurosaurs, a broad group that included raptors and even the ancestors of modern birds. These findings hinted that the theropods of Zealandia were not just isolated oddities, but part of the great web of dinosaur evolution. The environment these theropods lived in would have been lush and rich, with forests of conifers, ferns, and flowering plants spreading across valleys and uplands. Rivers flowed through the land, and coastlines were lined with swamps and deltas where dinosaurs could hunt or scavenge. In such settings, the theropods would have preyed upon herbivorous dinosaurs, perhaps small ornithopods or early relatives of the duck-billed dinosaurs. They may also have hunted young sauropods or scavenged from carcasses. The evidence suggests that theropods played an important role as apex predators, keeping populations of other dinosaurs in check and competing among themselves for food and territory. One of the most striking possibilities raised by fossil evidence is that Zealandia may have been home to raptor-like dinosaurs, similar in some ways to the velociraptors of Asia, but adapted to local conditions. These smaller theropods were built for speed and agility, with long legs, grasping hands, and sharp claws on their feet. They may have hunted in packs, ambushing prey in dense forests, or chasing them across open areas. Fossilized claws and bones found in New Zealand suggest that such creatures may have existed. Imagining a group of raptors darting through the greenery of Zealandia, communicating with calls and body movements as they coordinated a hunt, adds a vivid picture to the sparse fossil record. Larger theropods may also have roamed Zealandia, though direct evidence of giants like Tyrannosaurus has not been found. Instead, some fossils suggest the presence of medium-sized allosaur relatives that could have grown to lengths of several meters. These predators would have been formidable hunters, equipped with strong jaws, sharp teeth, and powerful limbs. They might have stalked the larger herbivores of Zealandia, striking with sudden attacks and tearing apart their prey. Even a small population of such predators could have influenced the balance of life across the continent. Since large carnivores typically require wide territories and abundant prey, the seas around Zealandia were equally rich with life, and theropods may have exploited these coastal areas for food. Some theropods are known to have eaten fish or scavenged along shorelines, and it is possible that New Zealand's ancient coasts saw predators hunting not only land animals, but also marine creatures. With the remains of plesiosaurs, mosasaurs, and other marine reptiles found in the same deposits as dinosaur fossils, it is not hard to imagine theropods scavenging washed-up carcasses or hunting smaller animals in tidal areas. This would have given them a flexible diet and allowed them to thrive in diverse environments. The rarity of dinosaur fossils in New Zealand makes each discovery precious. In the 1990s, for example, the discovery of bones in Otago led to heated discussions among scientists. Some argued that the bones belonged to theropods closely related to the coelurosaurs, while others thought they might belong to entirely different groups. Careful analysis of the bone structure revealed traits associated with carnivorous dinosaurs, including hollow bones and attachment points for strong muscles. These details helped confirm the presence of theropods in Zealandia, even if the exact species remain unknown. More recently, in the early 21st century, additional finds of isolated bones and teeth have continued to add to the evidence. What makes the theropod fossils of Zealandia especially intriguing is their link to the evolution of birds. Scientists now know that modern birds are direct descendants of theropod dinosaurs, specifically small feathered coelurosaurs. Fossil evidence from Zealandia includes bones that may have belonged to such bird-like theropods, suggesting that the ancestors of modern birds were present in this part of the world before the Great Extinction at the end of the Cretaceous period. This connection ties New Zealand's unique bird life, such as the kiwi and the extinct moa, to a much older lineage stretching back to meat-eating dinosaurs that once stalked the land. The isolation of Zealandia after it broke from Gondwanaland meant that its theropods and other creatures were cut off from populations elsewhere. This could have led to unique evolutionary paths, with Zealandia's predators developing special traits suited to their environment. Unfortunately, the incomplete fossil record makes it difficult to trace these changes in detail. Still, by comparing the few fossils from New Zealand with those from Australia, Antarctica, and South America, paleontologists can infer that similar groups of theropods existed across these southern lands, sharing a common ancestry before the continents drifted apart. The study of Zealandia's theropods also opens questions about how these predators survived in changing climates. During the late Cretaceous period, the world was warmer, and Zealandia would have had a temperate to subtropical climate with abundant rainfall. This created dense forests and wetlands, habitats that supported a variety of prey animals. Theropods in such environments might have relied on stealth and speed, blending into the shadows as they hunted. Their sharp senses of sight and smell would have given them an advantage, allowing them to track prey across long distances. Some may have been nocturnal hunters, using the cover of darkness to ambush unsuspecting animals. Although no complete skeletons of theropods have yet been uncovered in New Zealand, the potential for future discoveries remains high. Fossils are often hidden deep in rock layers or exposed only after erosion, landslides, or human excavation. Each new find has the potential to shed light on what kinds of theropods lived in Zealandia, how large they grew, and how they interacted with their environment. A single, well-preserved skeleton could reveal details about muscle attachment, movement, and even feathers, providing a clearer picture of these ancient predators. Paleontologists continue to search the coastlines, riverbeds, and quarries of New Zealand in hopes of uncovering such treasures. The presence of theropods in Zealandia adds another layer to the understanding of how dinosaurs spread and evolved across the globe. It shows that even in isolated corners of the world, meat-eating dinosaurs established themselves as dominant hunters. Their ability to adapt to different habitats and diets likely helped them thrive for millions of years. The traces left behind in Zealandia's rock serve as reminders of a time when predators with teeth like knives and claws like sickles hunted beneath the green canopy of ancient forests, their footsteps echoing in a world that has since vanished beneath the sea. The possibility that Zealandia hosted both small, raptor-like theropods and larger allosaur-type predators paints a vivid picture of a layered ecosystem. Small predators may have hunted insects, lizards, and small mammals, while larger predators tackled the bigger herbivores. Competition among theropods themselves could have been fierce, with different species carving out niches to avoid conflict. Some may have been solitary hunters, relying on stealth and strength, while others may have used cooperation and strategy to bring down prey. The dynamics of such interactions shaped the balance of life across Zealandia, even though the details are now locked away in stone. In addition to bones and teeth, fossilized footprints can also provide evidence of theropods. Although no clear theropod tracks have yet been widely reported in New Zealand, the possibility remains that such tracks exist, buried in ancient sediments, waiting to be uncovered. Footprints can reveal the size, speed, and behavior of dinosaurs in ways that bones cannot. A series of tracks might show a predator chasing prey, walking in groups, or moving across different types of terrain. If theropod tracks were ever found in Zealandia, they would offer direct evidence of how these animals lived and moved in their environment. The extinction event that occurred around 66 million years ago brought an end to the reign of the theropods, along with most other dinosaurs. Yet their legacy lived on in the form of birds, which survived and diversified in the millions of years that followed. The presence of theropod fossils in Zealandia ties New Zealand's modern wildlife to this deep history. The kiwi, with its small wings and nocturnal habits, may seem far removed from the deadly hunters of the Cretaceous. But genetically and anatomically, it is part of the same lineage. In this way, the fearsome theropods of Zealandia continue to live on in the forests and skies of New Zealand, even if only faint echoes remain of their once dominant presence. Long before the lands we know today took shape, when the seas were wider and the skies filled with strange winged creatures, the vast southern supercontinent of Gondwanaland was alive with giant animals. Among the most awe-inspiring were the sauropods, the long-necked giants whose size and grace captured the imagination of every person who has ever looked at their fossil remains. On the landmass that would one day break apart to form Zealandia, traces of these colossal plant-eaters have been found, giving us small but tantalizing clues about their existence on what is now a mostly drowned continent. These clues are rare and often fragmentary, But each discovery adds to a picture of a world that was far more diverse and vibrant than anyone once imagined. The sauropods were among the most extraordinary animals to have ever walked the earth. They stretched their necks skyward like living cranes, browsing on treetops that were unreachable to all other creatures. Their tails could sweep across the ground like enormous whips, and their bodies were supported by pillar-like legs thicker than tree trunks. Some species grew longer than 20 meters, others stretched over 30 meters, and there were even giants that may have reached close to 40 meters. To imagine such a being moving across the fern-covered valleys and conifer forests of Zealandia is to imagine a landscape of both wonder and strangeness. The fossils that suggest sauropods once lived on Zealandia are not complete skeletons. Instead, they're often single bones, fragments of vertebrae, or partial limb pieces, yet even these broken remains speak volumes. A single vertebra from a sauropod can be nearly a meter tall, with hollow chambers that show how these animals were built for both strength and lightness. In the late 19th century and throughout the 20th century, explorers and geologists working along the coast of New Zealand uncovered such bones embedded in ancient rock layers. Though many were puzzled at first, careful comparison with fossils from other continents revealed that these belonged to sauropods, tying Zealandia into the broader web of dinosaur life. The age of these fossils stretches back to the Mesozoic era, a span of time lasting from about 250 million years ago to about 66 million years ago. Within this great expanse, the Jurassic and Cretaceous periods were when sauropods reached their greatest diversity. During the Jurassic, around 150 million years ago, giants like Brachiosaurus and Diplodocus roamed the northern continents. By the Cretaceous, around 100 million years ago, titanosaurs had spread across nearly every landmass. The fossils in Zealandia suggest that its forests and floodplains were no exception, providing food and shelter for some of these immense creatures. The environment they lived in would have been lush and green, with conifers, cycads, and early flowering plants carpeting the landscape. The air was warm, the climate humid, and rivers meandered through valleys that were often lined with towering trees. For a sauropod, such conditions meant abundant food. With their long necks, they could strip branches high above the ground, while smaller dinosaurs grazed below. It is easy to picture herds of these giants moving slowly together, their massive feet sinking into the damp soil as they crossed the floodplains in search of fresh vegetation. One of the most remarkable aspects of sauropods is how they managed to grow so large. Fossils show that they had a unique system of air sacs connected to their lungs, similar to those found in modern birds. This system not only helped them breathe more efficiently, but also kept their enormous bodies lighter. Their bones were filled with hollows, reducing weight without sacrificing strength. On Zealandia, where the land was surrounded by shallow seas and volcanic activity, such adaptations may have been crucial, allowing the sauropods to thrive in habitats that shifted and changed over time. The connections between sauropod fossils in Zealandia and those found elsewhere tell us much about the ancient world. When Zealandia was still attached to Gondwanaland, animals could wander freely between regions that are now separated by oceans. A sauropod could have strolled from what is today South America across Antarctica and into Zealandia without ever encountering a sea. As Zealandia gradually drifted away from Gondwanaland around 85 million years ago, its dinosaur inhabitants became isolated. The sauropods that remained on this fragment of land may have evolved unique forms, adapted to local environments, though most evidence of such creatures lies hidden beneath the waves today. The discovery of sauropod bones in Zealandia also deepens the mystery of how these animals interacted with other dinosaurs. Fossils from New Zealand and nearby islands have shown that theropods, the meat-eating cousins of the sauropods, lived alongside them. These predators, some possibly related to the fierce Allosaurus or the later Tyrannosaurs, would have hunted juveniles or scavenged the remains of fallen giants. The balance between predator and prey shaped the ecosystem, ensuring that even the largest creatures were part of a complex web of life. To imagine the day-to-day existence of a sauropod in Zealandia is to picture a life filled with constant movement and constant eating. These giants needed enormous amounts of food to survive, perhaps hundreds of kilograms each day. Their peg-like teeth were designed not for chewing, but for stripping leaves, which they swallowed in great mouthfuls. Inside their massive guts, fermentation and bacteria broke down the plant matter, providing the energy they needed. Fossilized dung, known as coprolites from other parts of the world, shows that sauropods consumed everything from conifer needles to flowering plants, and it is likely the Zealandia species did the same. The young sauropods began life very differently from the towering adults. Fossil nests from South America and Asia show that sauropods laid dozens of eggs at a time, often in shallow pits scraped into the earth. The eggs were not very large compared to the adult size, often no bigger than a football. When the hatchlings emerged, they were vulnerable and tiny in comparison to their parents. Growing rapidly, they had to avoid predators and survive until their sheer size became a form of protection. In Zealandia, the survival of these young may have been even more precarious, as the land was fragmented and forests dense, hiding dangers at every turn. Some scientists believe that sauropods may have traveled in herds, not unlike elephants today, to protect their young. A herd of dozens of adults and juveniles moving together would have been a sight beyond imagination, the ground shaking beneath their combined weight. On the riverbanks of Zealandia, such gatherings may have left deep trackways, though many have since eroded away. Yet in other parts of the world, track sites with hundreds of footprints preserve the evidence of this behavior, and it is not difficult to picture similar scenes on the lost continent. The rarity of sauropod fossils in Zealandia is partly due to the geological history of the region. Much of the continent now lies submerged beneath the Pacific Ocean, and only a small fraction remains above water, as New Zealand and nearby islands. Rocks from the Jurassic and Cretaceous, where sauropod fossils might be preserved, are limited and often buried deep. This means that every discovery is precious, each bone or fragment a puzzle piece that must be carefully studied. When paleontologists identify a vertebra as belonging to a sauropod, it confirms not just the presence of a single animal, but an entire lineage that once thrived there. The fossils of sauropods have been compared to those of other continents, and striking similarities emerge. For instance, the titanosaurs of South America share certain traits with bones found in Zealandia, suggesting possible connections. Titanosaurs were among the last great sauropods, living until the very end of the Cretaceous around 66 million years ago. They were diverse, with some species covered in bony armor plates, while others were slender and graceful. It is possible that Zealandia was home to its own titanosaurs, species that have yet to be fully described. Comparisons with other giant animals also highlight the uniqueness of sauropods. No mammal, not even the largest whales, has ever combined such length, height, and terrestrial mobility. Sauropods were living skyscrapers, creatures that redefined the possibilities of life on land. Their existence on Zealandia ties this small fragment of the Earth's crust to a grand narrative of global prehistory, connecting it with Africa, Asia, and the Americas. Each fossil is a reminder that even the most remote corners of the planet were once part of a shared dinosaurian world. The link between sauropods and their distant ancestors adds another layer of fascination. They descended from smaller, more lightly built dinosaurs in the Triassic period around 230 million years ago. These early relatives were agile and swift, feeding on a variety of plants. Over millions of years, their descendants grew larger, Their necks and tails lengthened, and their bodies expanded to colossal proportions. By the time Zealandia broke away from Gondwanaland, sauropods had already conquered much of the Earth, their success unmatched among plant eaters. The sheer scale of these animals invites endless questions. How did they pump blood all the way to their brains, perched several meters above their hearts? Some scientists suggest that powerful hearts, weighing perhaps several hundred kilograms, kept the blood flowing. Others propose that their long necks were held more horizontally, reducing the strain. On Zealandia, where food may have been abundant but seasonal, such adaptations would have played a role in survival, allowing them to reach high or low vegetation as needed. Even the way sauropods move sparks wonder. Their tracks show that they placed their feet carefully, with forefeet that were more circular and hind feet that left crescent-shaped impressions. Some species walked with a wide stance, others with a narrow gait. On soft ground, their massive weight could create deep impressions, which later filled with sediment and hardened into stone. Though few trackways have yet been found in New Zealand, it is almost certain that such footprints once existed, only to be lost to erosion or submersion. The end of the sauropods on Zealandia came as part of a wider extinction event. Around 66 million years ago, a massive asteroid struck what is today the Yucatan Peninsula, unleashing global fires, darkness, and climate collapse. Like sauropods elsewhere, those on Zealandia would have perished, unable to cope with the sudden loss of vegetation and the breakdown of ecosystems. The seas rose, the forests vanished, and with them went the last of the long-necked giants. All that remains are the scattered bones and the silent testimony of rock. Yet the memory of these creatures lives on through study and imagination. Each fossil fragment found in Zealandia, no matter how small, connects us to a time when giants walked the earth. They inspire visions of towering animals silhouetted against the conifer forests, herds moving across mist-shrouded valleys, and hatchlings scrambling to survive in a dangerous world. Even beneath the waves, the continent still holds secrets, waiting for the patient work of paleontologists to reveal them. The continuing search for sauropod fossils in Zealandia brings excitement and anticipation. Scientists scour riverbanks, cliffs, and quarries, hoping to find more evidence. Advances in technology allow them to scan rocks for hidden bones, to model anatomy from fragments, and to compare DNA traces and sediments. Each discovery, however small, adds to the growing recognition that Zealandia was home to creatures as extraordinary as any found on other continents. As the sun sets over the mountains of New Zealand today, it is almost impossible to imagine that beneath those same skies, millions of years ago, long-necked giants once grazed and roamed. The rivers they drank from have shifted. The forests they fed upon have long since turned to stone, and the land itself has sunk beneath the ocean. Yet, in the bones weathering out of ancient rocks, their presence is still felt. They remain part of the story of Zealandia, silent giants whispering from the deep past, their echoes carried on waves and winds across the hidden continent. The picture of sauropods in Zealandia becomes far richer when we begin to imagine not just their bones and fragments, but their movements, their daily lives, their relationships with other dinosaurs, and the way they mirrored or diverged from their cousins in other lands. Fossil bones and rock layers may be silent, but by comparing what is known from other continents, paleontologists can paint a living portrait of how these long-necked giants might have thrived on the lost continent. It is a portrait full of drama, rhythm, danger, and survival in a world unlike anything alive today. A dawn in the ancient forests of Zealandia would have revealed a scene that was both peaceful and filled with hidden tension. The mist clung to the tree trunks, and the air carried the scent of damp leaves and resin. From a grove of tall conifers, a herd of sauropods stirred. Their massive bodies, some longer than a railway carriage, shifted and groaned as they rose from their resting spots. The ground itself trembled slightly with each step. These creatures moved slowly, not out of weakness, but because their weight and size demanded deliberate action. Their long necks swung gently, as if testing the air for scent or sound, before reaching upwards into the canopy. Leaves rustled and snapped as mouths stripped them from branches. Smaller dinosaurs scurried nearby, keeping close, but not too close. For where the sauropods grazed, fresh branches and shoots were left behind. Her life was central to many sauropods, and it is easy to imagine the same in Zealandia. Young ones, no taller than a man in their first years, clustered close to their mothers, using the towering bulk of the adults as living walls of protection. Juveniles moved with greater speed and curiosity, darting forward for a mouthful of ferns before hurrying back under the shade of a parent's belly. Adults communicated through low-frequency calls that vibrated through the ground, sounds too deep for the human ear, but felt like a distant rumble. These vibrations may have helped keep the herd together, even in the dense forests where visibility was poor. Other dinosaurs shared these forests. Small ornithopods with swift legs darted across clearings, feeding on low plants. The sauropods ignored them. Feathered theropods, some the size of turkeys, others as large as wolves, watched from the undergrowth. They were opportunists, scavengers, and hunters of the weak. Their keen eyes followed the hatchlings, waiting for a chance when one strayed too far from protection. For these carnivores, a sauropod hatchling was a prize worth great risk. The herd, however, was not defenseless. A single lash from a massive tail, swung with whip-like speed, could snap bones or send a predator flying. The daily life of a sauropod revolved around eating, moving, and resting. Their bodies demanded enormous quantities of food, and to satisfy this hunger, they would strip trees bare in a matter of hours before moving on. Their long necks allowed them to feed across multiple levels of the forest without expending much energy walking. Some may have stretched nearly vertical, plucking at branches 15 meters high, while others extended forward, sweeping through mid-level vegetation. The forest canopy was alive with movement as they fed, branches bending and snapping, leaves raining down to the ground where smaller creatures waited to take advantage of the leftovers. Water was equally important. Herds often gathered at riverbanks and lake shores, where their immense feet pressed deep impressions into the soft mud. These impressions, if preserved, could one day harden into fossils, recording their steps for millions of years. As they drank, smaller dinosaurs would gather too, careful to avoid the swinging necks and stamping feet of the giants. Crocodile-like reptiles may have lurked in the water, waiting for unwary juveniles, while giant dragonflies and early birds flitted above the rippling surface. The comparison with sauropods in other continents helps to bring these scenes in Zealandia into sharper focus. In South America, titanosaurs left behind entire nesting grounds with dozens of nests arranged close together. Each nest contained clutches of round eggs buried in soil or vegetation to incubate in the warm climate. It is very possible that Zealandia sauropods practiced the same behavior. Imagine the clearing of a fern meadow filled with shallow pits, each marked by the rounded forms of eggs, with mothers standing guard at the edges while smaller predators circled in the shadows of the forest. The hatchlings, when they emerged, would face a perilous journey from the very first day. Fossilized embryos in some eggs from Argentina show that young sauropods were already developing the traits they would need to survive, such as strong legs and partially formed teeth, ready to begin the endless work of feeding and growing. In Africa, sauropod fossils, such as those of Brachiosaurus, suggest that these giants sometimes lived in semi-arid environments, feeding on scattered trees across open plains. By contrast, Zealandia during much of the Cretaceous was humid and covered with lush vegetation. This difference may have influenced not only the types of sauropods that lived there, but also their behavior. In wetter environments, herds may not have needed to travel as far to find food. Instead, they moved within smaller ranges, returning to the same floodplains season after season. This would have created well-trodden paths, muddy routes cut deep into the earth by repeated use, similar to elephant trails in Africa today. Asia, too, provides parallels. In Mongolia, sauropods such as Nemegtosaurus lived alongside ferocious predators like Tarbosaurus, a cousin of Tyrannosaurus rex. In Zealandia, the predators may not have grown quite so large, but they were certainly present. The balance between herbivore and carnivore shaped every interaction, with sauropods constantly aware of threats to their young. Even though an adult sauropod was nearly untouchable, the herd as a whole had to remain vigilant. This constant tension would have been part of daily life, a rhythm of feeding, moving, and watching. The social behavior of sauropods remains a subject of fascination, and Zealandia's herds would have been no exception. Fossil trackways in North America show parallel lines of footprints from multiple individuals, suggesting coordinated movement. Some scientists believe that sauropods may have organized themselves by size, with adults taking the lead and juveniles following in the center for protection. Others propose that herds were loose gatherings, with individuals moving in and out as they pleased. On Zealandia, perhaps herds of 30 or 40 giants moved together across the landscape, their combined presence altering the very shape of the ecosystem. Nightfall brought new dynamics. The temperature dropped, and the forest grew darker, filled with the calls of nocturnal creatures. The sauropods would settle, some standing, others lying down carefully on their sides, their bulk pressing deep into the ground. Smaller dinosaurs became more active, darting between the shadows in search of insects or carrion. Predators prowled more boldly, knowing that darkness provided cover. A lone juvenile wandering too far from the group might have fallen victim to a pack of theropods, its cries lost in the rustle of the trees. For the survivors, dawn would bring another cycle of movement and feeding, life repeating itself in an endless rhythm. The comparison with other continents also reveals the vast range of sauropod diversity. In South America, species like Argentinosaurus grew to nearly 40 meters, towering giants that stretched the limits of terrestrial size. In Europe, smaller sauropods like Europasaurus evolved in island environments. Their size reduced because of limited resources. Zealandia itself, as a continent surrounded by seas and broken into islands, may have given rise to unique forms as well. Perhaps its sauropods were slightly smaller than the South American giants, shaped by the constraints of their environment. Or perhaps, hidden beneath the sea, there are fossils waiting to show that true giants once roamed here as well. The physiology of these creatures adds further color to their daily lives. Their long necks were not rigid, but flexible, composed of numerous vertebrae with complex joints. They could sweep across wide arcs, feeding in many directions without moving their massive bodies. Their tails, equally flexible, may have been used for balance, defense, or even communication, cracking through the air like whips. The sounds of a herd in motion would have been overwhelming. The creak of trees breaking under their weight, the rumble of their calls, the crashing of branches, and the heavy thuds of their footsteps. On Zealandia, where the land was volcanic and rivers often shifted course, these sounds would have mingled with the roar of eruptions and the rush of floodwaters, creating a landscape alive with noise and power. Even the act of reproduction shaped their interactions. During breeding seasons, males may have displayed their strength through neck wrestling or booming calls that echoed through valleys. Females selected nesting sites carefully, choosing areas safe from floods yet close to food. These nesting grounds became focal points of activity, attracting not only the sauropods themselves, but also scavengers, predators, and smaller creatures looking to steal eggs. The struggle for survival was present at every stage, from egg to adult, ensuring that only a fraction of the young would ever grow to full size. Across continents, sauropods showed remarkable resilience. They survived for more than 100 million years, adapting to changing climates, shifting continents, and evolving predators. In Zealandia, their story was part of this greater saga. Though only fragments remain to tell it, those fragments carry echoes of daily life: herds grazing at dawn, hatchlings scrambling from nests, predators circling in the shadows, and giants moving endlessly across a green and ancient land. Seasonal change in ancient Zealandia would have carried a rhythm that shaped the lives of its inhabitants, and the sauropods, with their endless need for food and water, were among the most attuned to these cycles. Though the climate in much of Zealandia during the Cretaceous was warm and humid, there were still fluctuations of wet and dry, shifts of flood and drought, and the seasonal flowering of plants. These changes would have guided the herds across the continent, pushing them from one fertile valley to another, from low floodplains to higher ground, and sometimes even towards the coast, where new feeding grounds awaited. Picture a herd of perhaps 30 sauropods, their long necks swaying in unison as they crossed a wide plain. The air shimmered with summer heat, and the grasses had grown dry and brittle. The once green ferns along the riverbank had withered, leaving little for the giants to eat. Driven by hunger, they began to move, their massive bodies trudging slowly but steadily toward the distant foothills, where the scent of conifers still drifted on the wind. The migration was not swift, for such animals could not rush, but it was relentless. Day after day, the herd pressed onward, leaving behind deep impressions in the soil and clouds of dust that hung in the air. Along the way, they encountered other dinosaurs. Herds of smaller ornithopods grazed the dry grasses, scattering like startled birds as the sauropods advanced. Packs of theropods shadowed the herd, watching for signs of weakness, focusing on the young and the sick. But the unity of the sauropods, their sheer numbers and colossal presence, deterred direct attack. Only when the herd grew weary and a calf fell behind would the predators surge forward, their cries echoing across the plains in a brief but violent moment of struggle. The migrations carried the sauropods not only across plains and valleys, but sometimes toward the coastal regions of Zealandia. Here, the land met the shallow seas in wide estuaries and tidal flats. The salt air mingled with the scents of seaweed and brine, and the calls of seabirds pierced the wind. The sauropods, thirsty and hungry, would find fresh growth along the coastal margins, where river sediments nourished lush vegetation. They would stand at the edge of the sea, dipping their heads to drink from freshwater pools, their massive forms reflected in the shallows. It was here, at the meeting of land and sea, that the giants of the land may have encountered the giants of the water. Just beyond the breakers, enormous marine reptiles prowled. Mosasaurs, with jaws full of conical teeth, glided through the waves, their long tails propelling them like serpents. Plesiosaurs, with swan-like necks and paddle-shaped flippers, rose to the surface, their heads breaking the waves before slipping silently back into the depths. Though these marine reptiles posed no threat to a full-grown sauropod, a calf that strayed too close to the water's edge could have drawn their attention. One can imagine the sudden splash, the cry of alarm, and the frantic retreat of the herd as a young sauropod vanished beneath the waves, claimed by a predator of the sea. The coast was a place of both danger and opportunity. As the tides ebbed, they revealed stretches of seaweed and hardy plants, which the sauropods may have nibbled at in times of need. Fossil trackways in other parts of the world show sauropods wading into shallow waters, their great bodies buoyed slightly by the waves. Perhaps Zealandia's sauropods did the same, stepping cautiously into estuaries to feed on aquatic plants, their long tails trailing in the surf as marine reptiles watched from a distance. The migrations were not only about survival, but also about shaping the land itself. The constant movement of herds left visible marks on the environment. Trails carved through the forests became open corridors, used again and again by subsequent generations. Trees were stripped bare of leaves, where sauropods paused to feed, and young saplings were trampled underfoot. Over time, these feeding habits reshaped entire landscapes. In places where sauropods returned season after season, forests may have opened into clearings, creating spaces where sunlight reached the ground and new plants flourished. Their dung, produced in massive quantities, fertilized the soil, enriching it with nutrients. Seeds swallowed, along with leaves, passed through their digestive tracts and were dropped far from their original source, carried across valleys and rivers by migrating herds. In this way, sauropods acted as gardeners of the land, spreading plants and shaping the very composition of Zealandia's forests. A single herd could influence ecosystems across hundreds of kilometers, their presence echoing in the growth patterns of plants long after the animals had moved on. The seasonal cycle also brought floods, and here too the sauropods played their part. When rivers swelled with rain and overflowed their banks, herds would be forced to move to higher ground. As they crossed muddy floodplains, their weight churned the soil, mixing layers and creating impressions that might one day be preserved as fossils. Their footprints, pressed deep into the earth, could be filled with silt and sand, capturing the moment in stone. In places where multiple herds crossed, these floodplains became vast record books of ancient life, layered with prints of giants moving across the wet ground. In imagining their interactions with the forests, it is easy to compare them to elephants of today. Just as elephants knock down trees to reach branches, sauropods may have pushed against trunks with their shoulders, toppling smaller trees to access fresh growth. Whole groves may have been reshaped by their feeding. Ferns and shrubs flourished in the open light left behind, while the fallen trunks provided homes for insects and smaller animals. The sauropods were ecosystem engineers, their immense appetites continually sculpting the land. Other continents offer glimpses of how this shaping might have looked. In North America, evidence suggests that sauropods like Diplodocus grazed at different levels of vegetation than Brachiosaurus, dividing the forest into feeding zones. In South America, titanosaurs lived in dense herds that stripped vegetation in sweeping waves, leaving behind landscapes dotted with trampled clearings. If similar patterns held true in Zealandia, then its forests may have been mosaics of growth, with tall stands of untouched trees in one place, open meadows in another, and regenerating clearings elsewhere. The very forests themselves bore marks of these interactions. Fossilized tree trunks from New Zealand show growth rings that speak of cycles of stress and recovery, perhaps reflecting the seasonal feeding pressures of large herbivores. Certain plants may have even evolved defenses against heavy browsing, such as tough leaves or rapid regrowth, shaped by millions of years of coexisting with giants. The relationship between sauropods and plants was a dialogue written in growth and consumption, resilience and adaptation. The migrations also linked different environments together. Herds moving inland connected the coastal ecosystems with the deep forests, carrying seeds, nutrients, and disturbances across wide distances. In this way, sauropods were not just inhabitants of Zealandia, but active participants in weaving its ecological fabric. Their daily choices of where to move and what to eat rippled outward, influencing everything from insect populations to the distribution of trees. In the broader context, comparing these patterns with other continents reminds us of the universality of sauropods. In Africa, they shaped savannas and river valleys. In Asia, they influenced arid deserts and lush floodplains. In South America, they dominated nesting grounds and reshaped forests. On Zealandia, their role would have been just as profound, even if much of the evidence now lies hidden beneath the sea. The bones and fragments we uncover today are more than just relics. They are hints of migrations that reshaped valleys, of encounters at the edges of the sea, of forests that grew and regrew under the pressure of enormous appetites. The lost continent, half buried beneath the Pacific, still carries those echoes, Every bone lifted from the rock is a whisper of movement across seasons, of herds marching from forests to coasts and back again, of long necks stretching skyward as marine reptiles glided silently just beyond the breakers, and of forests forever changed by the gentle but relentless feeding of the long-necked giants. Armored defenders, the great living tanks of the age of dinosaurs, may have once walked across the lands of Zealandia before most of that vast continent sank beneath the waters. When people speak of armored dinosaurs, the first kind that comes to mind are the ankylosaurs, with their heavy plates, bony spikes, and club tails. These creatures were unlike most others, not swift runners like theropods, not towering plant eaters like sauropods, but low to the ground, wide and heavily built, as if nature had decided to forge its very own war machine. To imagine such animals in Zealandia is to imagine a land where the forests and river valleys were not only filled with tall, browsing giants and fierce hunters, but also with squat, slow-moving, heavily shielded creatures that carried their defense with them at all times. The possible presence of ankylosaurs in Zealandia has been suggested because of scattered fossil evidence, fragments of bone and armor plates that hint at their existence. These pieces are not whole skeletons, not enough to say for certain, but enough to whisper of a time when armored defenders trundled through the undergrowth, tearing ferns and cycads from the ground with their beaked mouths. Ankylosaurs were a group spread across many continents during the Cretaceous period, from Asia to North America, from Europe to South America. And it would not be strange if Zealandia, too, had harbored its share of these resilient plant eaters. These dinosaurs were built close to the earth, with wide bodies and strong legs that supported their heavy frames. Across their backs grew a mosaic of bony plates called osteoderms, each one fused into the skin like a natural suit of armor. Some ankylosaurs bore spikes jutting out from their sides to ward off attackers, while others had tails tipped with great clubs of solid bone that could swing with enough force to break a predator's S-leg. The image of such a creature standing firm against a lunging theropod, tail raised and ready to strike, is both dramatic and awe-inspiring. If Zealandia had theropods, which fossil finds suggest it did, then armored defenders would have been a perfect counterbalance, plant eaters that did not flee in panic but stood their ground. The ecosystem of Zealandia during the time of the dinosaurs was likely a patchwork of forests, swamps, river valleys, and open plains. Ankylosaurs would have fit well into this environment. They were not fast enough to chase after food like carnivores, not tall enough to reach the upper branches like sauropods. Instead, they grazed low plants, stripping ferns, cycads, and other ground-level vegetation. Their beaks and leaf-shaped teeth were perfect for shearing and grinding plant matter, turning dense foliage into fuel for their stout bodies. In this way, they shaped the undergrowth, keeping it trimmed and influencing what kinds of plants could grow. By eating vast amounts of low vegetation, ankylosaurs may have cleared pathways in the forests, opening up space for other plants to spread. Their constant grazing would have created habitats for smaller animals, such as lizards, mammals, and insects, that thrived in more open ground. The droppings of these large herbivores would have fertilized the soil, spreading nutrients and seeds alike, and helping the cycle of life continue. Their armored bodies may have moved slowly, but their role in shaping the land was far from minor. Imagine a scene along a riverbank in ancient Zealandia. The morning mist rises from the water, and towering conifers stretch into the sky. Beneath them, ankylosaurs shuffle about, scraping at tough plants with their beaks. Their backs glisten with dew that clings to their bony armor. Youngsters stay close to the adults, learning which plants are safe to eat. A distant roar echoes from the forest, a theropod on the hunt. But the ankylosaurs do not scatter. They close ranks, tails twitching, heads low, spikes and plates forming a wall of defense. The predator knows that attacking one of these living fortresses is risky, for a single strike from a tail club could mean broken bones, and so the predator slips away, seeking easier prey. In this way, ankylosaurs shifted the balance between hunter and hunted, forcing carnivores to think twice before striking. The evolution of ankylosaurs was a story of defense perfected. Over millions of years, they grew heavier, broader, and more armored. Early forms were less protected, with smaller plates and weaker tails. But as time passed, their shields thickened and the tail club became more pronounced. This adaptation must have been incredibly useful in regions where predators grew ever more fearsome. In Zealandia, where theropod tracks and bones tell of sharp-toothed hunters, the presence of ankylosaurs would have been a natural response in the arms race of survival. Even without complete skeletons, the fragments found in New Zealand and surrounding regions suggest that armored dinosaurs may indeed have been part of the ecosystem. Paleontologists have unearthed isolated bones that bear resemblance to ankylosaur remains found elsewhere, hinting at connections between Zealandia and other landmasses. This fits with what is known about the ancient world, for during the Cretaceous period, Zealandia was still connected by shallow seas and island chains to parts of Gondwanaland. Animals could have spread across these routes, populating new lands before continental drift, and rising waters cut them off. Ankylosaurs, though heavy and slow, could still have reached Zealandia through these land bridges, establishing themselves in its forests and valleys. Ankylosaurs were not only defensive, but also social creatures. Some evidence from trackways in other parts of the world suggests they may have moved in groups, perhaps family units or small herds. If they did the same in Zealandia, one could picture processions of armored dinosaurs moving together, their footsteps shaking the ground, their armor gleaming in the sunlight filtering through the trees. Such gatherings would have been a sight both majestic and intimidating, for even the fiercest predator would think twice before attacking a cluster of living tanks. The young ankylosaurs, though not yet fully armored, would have been protected by the presence of adults. As they grew, their bodies hardened and plates formed across their backs. By the time they reached maturity, they were nearly impregnable, their only vulnerable points being the softer underbelly or the throat, places difficult for predators to reach. In this way, ankylosaurs represented one of the most successful survival strategies of their time, not through speed or cunning, but through endurance and fortification. The ecology of Zealandia would have been richer for their presence. Their constant grazing patterns shaped the plant life, and their armored bodies influenced predator behavior. They likely competed with other herbivores, such as hadrosaurs, which nibbled higher plants, and smaller ornithopods, which may have darted among the undergrowth. This balance of eaters meant that vegetation was used at all levels, from the ground ferns up to the tallest tree branches browsed by sauropods. Ankylosaurs claimed the middle ground, low but powerful, consuming the tough plants that others may have ignored. In terms of appearance, ankylosaurs were creatures of striking form. Their bodies were squat, wide, and muscular. Their heads were low, with beaks strong enough to cut through tough vegetation. Rows of armored plates lined their backs, some shaped like flat shields, others like spikes. The tail, thick and muscular, ended in a massive club of bone, a weapon as formidable as any found in nature. Some species had nostrils placed high on their snouts, possibly to help them breathe while feeding low to the ground. Their eyes, though small, were keen enough to watch for movement, for even an armored giant had to remain alert. Their behavior must have been slow and deliberate. They likely spent much of the day foraging, moving from patch to patch of plants, grinding their food with leaf-shaped teeth. Digestion would have been a long process, their large guts fermenting the tough plant matter. Resting under trees, they may have been seen lying quietly, their armor plates blending with the rocky ground, giving them camouflage as well as protection. At night, they may have huddled together, tails forming a circle of defense against nocturnal predators. The role of ankylosaurs in the food web was crucial. They were prey in theory, but not in practice, for few predators dared to attack them. This gave them a unique place, allowing them to consume vast amounts of vegetation largely undisturbed. Their size and armor meant they could live long lives, spreading their kind across the land. And when they died, their bodies became rich sources of food for scavengers, their tough armor plates lying scattered on the ground like pieces of broken stone. The fossils that suggest their presence in Zealandia may be few, but they carry great weight. Even a single piece of ankylosaur armor tells a story of adaptation and survival, of a creature that stood its ground in a world of giants and hunters. These remains remind us that the lost continent beneath the ocean once held wonders beyond counting, with armored defenders moving slowly but surely through its forests. The possible ankylosaurs of Zealandia connect this land to a greater web of life that stretched across Gondwana land. Their ancestors may have come from South America or Antarctica, crossing into Zealandia when climates were warmer and seas were lower. Once established, they would have adapted to the unique environments of this region, perhaps developing features not seen elsewhere. Some might have been smaller, suited for dense forests, while others could have been larger, thriving in open plains. Their diversity may have been as rich as that seen in North America and Asia, where dozens of ankylosaur species once lived. Life in Zealandia would not have been easy. Shifting climates, volcanic activity, and changing sea levels shaped the land constantly. Ankylosaurs, with their heavy builds, had to endure these challenges while still avoiding predators and competing for food. Their armor gave them an advantage, but it also made them slow, so they could not wander far in search of new feeding grounds. This meant they had to live where plants were plentiful and reliable, in fertile valleys and along rivers where growth was constant. Their movements may have followed seasonal patterns, staying near water sources during dry times and spreading out when rains returned. The sounds of ankylosaurs may have been deep and rumbling, vocals that carried through the forest to communicate with one another. Some scientists believe they may have had resonating chambers in their nasal passages, allowing them to produce such sounds. These calls could have warned of danger, guided young, or helped keep herds together. In the dim light of dawn or dusk, one can picture their forms moving slowly through the mist, their heavy steps shaking the ground, their calls echoing softly among the trees. Even their enemies respected them. Theropods, though armed with sharp teeth and claws, would have known the risk of attacking a fully grown ankylosaur. A tail club swinging with force could shatter bones, leaving a predator crippled. Perhaps only the desperate or the reckless would have dared strike at such a foe. More often, predators would have stalked smaller, swifter herbivores, leaving the armored defenders to feed in relative peace. This uneasy balance kept the ecosystem stable, each creature playing its part in the grand cycle of life. The possible ankylosaurs of Zealandia, though only hinted at by fossils, spark the imagination of what once was. A lost continent, mostly drowned, once filled with forests, rivers and plains, where armored giants lived alongside hunters and towering plant-eaters. Their role was not minor, but essential, shaping the land through their feeding, standing as bulwarks against predators, and carrying the story of evolution's creativity. To picture them is to bring back a time when Zealandia was alive with thunderous footsteps and the clash of survival. Picture the ancient land of Zealandia during the late Cretaceous period, a landmass that was larger than modern-day India and only later sank beneath the sea. Back then, it was alive with forests of tall conifers, cycads, ferns and flowering plants that had only recently begun to spread. Rivers wound through valleys, wetlands shimmered under the sun, and coastal regions bore sandy shores where marine reptiles ruled the waves. Into this setting, we place the armored defenders, the ankylosaurs, whose very bodies were built to endure in a dangerous world. Ankylosaurs were never graceful in the way of the long-necked sauropods that could sway through trees, nor swift like the sharp-clawed theropods that hunted with deadly speed. Instead, they embodied strength, weight, and patience. In Zealandia, they would have moved slowly, their wide feet pressing into damp soil, leaving behind footprints shaped like rounded impressions. In the stillness of the forest, one might hear the crunch of vegetation as they fed, the sound of branches snapping beneath their bulk, or the soft scrape of their armor as they brushed past tree trunks. The environment of Zealandia was unlike the deserts of Mongolia, where famous ankylosaur fossils have been found, or the broad river plains of North America, where armored dinosaurs like Ankylosaurus itself once lived. Zealandia was moist, forested, and mild in climate. Ankylosaurs that lived there would have been adapted to dense woodlands, using their strong bodies to push through thickets. Unlike their desert-dwelling cousins, they would have fed not on sparse shrubs, but on lush carpets of ferns, soft undergrowth, and the lower leaves of cycads and angiosperms. Their diets may have included tougher plants too, for their beaks were strong enough to shear through fiber-rich stems, and their teeth, though small, were efficient at grinding. To walk among these creatures would have been like walking among living fortresses. Their skin was covered in osteoderms, the bony plates that grew out of their dermis. Each plate was unique, some broad and flat, others raised into knobs or spikes. In some species, these plates fused together into near impenetrable shields, while in others, they remained separated, forming a mosaic pattern. The ankylosaurs of Zealandia may have developed their own variations, perhaps with smaller, more rounded armor to maneuver more easily among trees. Yet always their design was defense first, offense second. The tail club of an ankylosaur is perhaps its most famous feature. Made of fused vertebrae at the tip, surrounded by heavy bone growths, it was like a mace that could swing with enormous force. Muscles along the tail's length allowed it to be raised and whipped sideways, delivering crushing blows. In North America, paleontologists believe these clubs could break the leg of a tyrannosaur. In Zealandia, they may have served a similar purpose against local predators. Imagine a theropod charging, jaws open wide, and the ankylosaur swinging its tail like a hammer. The clash of bone on bone would resound through the forest, and the predator, stunned or crippled, would limp away. This weapon gave ankylosaurs a sense of power rare among herbivores, allowing them to stand their ground in a world ruled by teeth and claws. The presence of such a creature in Zealandia would have reshaped predator behavior. Hunters would have learned quickly that ankylosaurs were costly prey, not worth the risk when smaller, softer-bodied animals existed. This meant ankylosaurs influenced which animals were eaten and which survived, subtly guiding the rhythm of predation. The very act of existing as a walking fortress meant they changed the choices of carnivores. This indirect effect rippled through the ecosystem, altering who lived, who died, and how energy flowed through the land. Their role as grazers was equally important. By feeding on tough plants, ankylosaurs kept the understory in check. Forest floors that might otherwise have been tangled jungles were instead opened into pathways where light could filter through. Smaller herbivores like hypsilophodons may have benefited from these open corridors, darting in and out of spaces cleared by ankylosaurs. Even their dung played a part, spreading seeds and enriching soils. In this way, they were gardeners of the forest, shaping the very land beneath their feet. Comparisons with ankylosaurs on other continents make the possible Zealandian forms even more fascinating. In North America, species like Ankylosaurus and Euoplocephalus were massive, some stretching over 6 meters in length, with tails that swung like battering rams. In Asia, forms like Pinacosaurus lived in sandy deserts, smaller in size but agile among dunes. In South America, fossils hint at a group called Nodosaurids, relatives of ankylosaurs without tail clubs but covered in long spikes. Each continent shaped its armored defenders differently, molding them to match the landscape and predators they faced. Zealandia, with its forests, wetlands, and unique isolation, may have produced its own distinct armored forms, creatures smaller or larger, spikier or rounder than any found elsewhere. It is possible that ankylosaurs in Zealandia bore similarities to Antarctic relatives, for Zealandia and Antarctica were once closer. Fossil evidence from Antarctica has shown that armored dinosaurs lived even in polar regions, enduring months of darkness and cold. If ankylosaurs could survive there, then Zealandia's temperate forests would have been even more suitable. Perhaps Zealandian ankylosaurs carried adaptations for damp conditions, such as armor that resisted moss growth, or behaviors that led them to bask in sunlight to dry after rains. To imagine their lives more vividly, consider a day in the life of a Zealandian ankylosaur. At dawn, when the first light pierces the canopy, a herd stirs from rest. They move slowly to a riverbank, their heavy steps pressing tracks into soft mud. They drink deeply, their armored reflections shimmering in the water. Youngsters, smaller and less armored, splash clumsily near the shore, watched over by adults. Then feeding begins. Long hours spent stripping low plants, chewing, swallowing, and moving on. Their jaws work constantly, the sound of grinding carrying softly. When danger approaches, perhaps the faint sound of a predator moving through underbrush, the herd tightens, heads low, tails outward. The tension is thick, but often no battle follows, for the sight of so many armored bodies is enough to discourage attack. As the sun climbs high, they rest in shade, their armored backs heating in shafts of light. Insects crawl across their plates, birds perhaps perching to pick at parasites, a miniature ecosystem living atop these moving fortresses. Toward evening, they move again, seeking new patches of plants. Their calls, deep, rumbling, almost seismic, keep them in contact. By nightfall, they lie down together, their massive bodies like boulders strewn in the forest. They sleep, but even at rest, they remain formidable, for any predator would find them a nearly impossible challenge. Fossilized trackways in other parts of the world show that ankylosaurs could leave long trails across muddy flats. If such trackways existed in Zealandia, they would show the passage of groups, families, or herds moving together. Each footprint would be a rounded depression, sometimes with faint impressions of claws. To walk along one of these ancient trails would be to follow the path of armored defenders long gone, to sense their weight pressing into the earth millions of years ago. The differences between ankylosaurs and other herbivores also highlight their uniqueness. Hadrosaurs, the duck-billed dinosaurs, relied on speed and numbers, fleeing predators rather than fighting. Sauropods relied on size, their sheer bulk making them difficult targets. Ceratopsians, in regions where they lived, bore horns and frills for defense. But ankylosaurs specialized in armor, carrying protection so complete that even the fiercest predator hesitated. This strategy worked across continents, from deserts to forests to icy lands, showing the success of their design. In Zealandia, this same design would have brought stability to the ecosystem, a constant presence among the more dynamic animals. Even their death held meaning. When an ankylosaur died, its body was so heavily armored that scavengers struggled to break through. Sometimes carcasses floated into rivers, carried downstream, where their armor eventually sank them. Fossils of ankylosaurs in other continents are often found belly up, their heavy backs pulling them down in water. If this happened in Zealandia, armored bones may lie beneath ancient sediments waiting to be uncovered. Each plate and spike tells a tale of resilience, each fossil a fragment of a world once alive with armored defenders. The connection of ankylosaurs to Zealandia also ties into the story of continental drift. When Zealandia broke away from Gondwanaland around 85 million years ago, it carried with it a collection of life forms. Some of these animals thrived, some dwindled, and some evolved into unique forms. Ankylosaurs, if present, would have been among the Gondwanan heritage, spreading from South America or Antarctica into Zealandia before the seas cut them off. Once isolated, they would have followed their own evolutionary path, distinct from the ankylosaurs of Asia or North America. This isolation could have produced strange and wonderful adaptations, perhaps smaller body size for dense forests, or armor patterns different from anything known elsewhere. The imagery of armored defenders in Zealandia is powerful, for it shows a land not just of hunters and giants, but of resilience and defense. These creatures, slow yet steady, armored yet vulnerable in rare ways, filled a niche that no other dinosaur could. They were guardians of the ground layer, keepers of the undergrowth, and living fortresses against predators. Their possible presence in Zealandia adds richness to the vision of this lost continent, suggesting that even in isolation, nature's grand experiments in survival played out in full. To imagine ankylosaurs in Zealandia is to bring back to life a place where survival was written not in speed or in sheer size alone, but in the steady rhythm of armored strength. These animals were not meant to chase nor to flee, but to endure. They were slow, yes, but not weak. They were heavily built, yes, but not clumsy. They were designed for balance, to feed low, to travel steadily, to protect themselves from all sides, and to leave behind a presence that changed the landscape in ways subtle yet immense. Their very existence, even if only glimpsed through scattered fossils in Zealandia, tells of a land that must have echoed with the heavy tread of armored defenders moving through ancient forests. The fragments that suggest their possible presence in Zealandia are like whispers through deep time. A single piece of armor, shaped like the bony osteoderm seen in ankylosaurs elsewhere, carries a story of connection. A bone shaped in a way that fits the pattern of ankylosaurs opens a doorway into speculation. These fossils are not complete skeletons like those uncovered in Mongolia or Alberta, but even in their partial state, they are windows into a hidden chapter of Zealandia's past. If ankylosaurs truly lived there, then Zealandia's ecosystems were richer and more varied than we can fully grasp, with armored defenders lumbering alongside hadrosaurs, sauropods, and carnivorous theropods. Behavior of ankylosaurs can be reconstructed not from Zealandia alone, but from their relatives across Gondwanaland and Laurasia. On every continent where their remains are found, ankylosaurs reveal similar lifestyles, yet also unique adaptations. In North America, species like Ankylosaurus magniventris lived at the very end of the Cretaceous. Huge animals measuring more than 6 meters in length, with tails tipped in massive clubs. These were the epitome of the armored defender design, perfected against predators like Tyrannosaurus rex. In Asia, in the Gobi Desert, paleontologists have uncovered Pinacosaurus, smaller but abundant, often found in groups of juveniles that may have died together. These fossils suggest that ankylosaurs were not loners, but lived in herds or family groups, their young learning from the safety of numbers. In South America, a different lineage, the Nodosaurids, carried armor but lacked the tail club, instead bearing long spikes along their flanks for defense. These differences show that armor could take many forms, each shaped by environment and predator threats. If Zealandia held ankylosaurs, which form did they take? Perhaps they were closer to Nodosaurids, with spikes instead of clubs, adapted for pushing through dense undergrowth. Or perhaps they carried full tail clubs, standing firm against the theropods that prowled Zealandia's forests. The exact form is lost to time, but the very possibility invites visions of strange hybrids, creatures with features unlike their cousins elsewhere, forged by isolation and the specific pressures of Zealandia's ecosystems. Behaviorally, ankylosaurs were steady creatures. Their lives revolved around feeding, resting, and avoiding predators. They woke with the rising sun, grazing among ferns and cycads, biting through stems with their beaks, grinding plants with their small, leaf-shaped teeth. Their guts were large fermentation chambers, breaking down tough cellulose with the help of bacteria, producing heat and energy for their massive bodies. They did not chase after food, nor did they fight constantly. Their strategy was patience, consuming steadily, conserving energy, moving when necessary, resting when full. In their slow rhythm, they maintained balance, not depleting plants too quickly, but constantly trimming the growth, keeping underbrush controlled. Their social lives must have been rich, though the fossils cannot tell us everything. Tracks found in North America show multiple ankylosaurs moving together, suggesting group behavior. Pinacosaurus fossils of juveniles buried together in Asia strengthen the case for herding, at least among the young. In Zealandia, this could mean herds of armored defenders roaming together, parents protecting their offspring within the group, tails outward in defensive circles at night. Imagine such a sight. A dozen armored bodies resting side by side in the moonlight, their backs gleaming like stone in the soft glow, their tails forming a ring of deterrence. Predators would have been wise to give such a gathering a wide berth. The defenses of ankylosaurs were not passive alone. The tail club was not merely a threat, it was a weapon. Studies of muscle attachment sites on ankylosaur tails show that these animals could swing with tremendous force, delivering blows strong enough to break bone. A predator that dared to attack risked losing mobility, for a shattered leg meant death by starvation. In Zealandia, where theropods may have reached formidable sizes, ankylosaurs with clubs would have been essential. They would not have run from danger. Instead, they would have turned, lowered their heads, and swung, ready to strike. This act of defiance reshaped predator-prey dynamics, for carnivores often hunt the weakest or easiest targets. Ankylosaurs, covered in bone and armed with clubs, were rarely the easiest. The comparison between ankylosaurs and other herbivores is telling. Sauropods, like the titanosaurs of Gondwanaland, relied on sheer size, growing so massive that predators struggled to bring them down. Hadrosaurs relied on speed and large herds, fleeing in waves when attacked. Ceratopsians, in regions where they lived, carried horns and shields, facing predators head-on. Ankylosaurs chose a different path, slow but unyielding, small in height but immense in protection. This made them unique in the ecosystems of the Cretaceous. In Zealandia, their role would have complemented that of other herbivores, filling the ecological niche of low-level browsers who could withstand attack. Fossil evidence, though sparse in New Zealand and broader Zealandia, remains suggestive. In South Island, discoveries of isolated dinosaur bones have been reported, including fragments that resemble those of armored dinosaurs. In some cases, these may represent ankylosaurs, though the evidence remains debated. The ocean has hidden much of Zealandia's past beneath sediments, leaving us with only hints, only fragments carried by rivers into deposits that have survived erosion. Each new find holds the potential to rewrite the picture, to add flesh to the shadows of armored defenders. Comparisons with Gondwanan relatives bring the story further into focus. In Antarctica, ankylosaur fossils have been discovered, showing that these creatures could survive even in polar conditions. This is remarkable, for it suggests adaptability far greater than once assumed. If ankylosaurs could endure months of darkness and cold, they could certainly thrive in Zealandia's temperate climate. The connection between Antarctica and Zealandia was real during the Cretaceous, with land bridges and shallow seas allowing movement. Ankylosaurs may have crossed into Zealandia during these times, spreading into its forests and valleys. Once isolated, they may have evolved into distinct forms, much as New Zealand's modern birds evolved into unique species after isolation. In Laurasia, ankylosaurs reached their zenith with species like Ankylosaurus in North America and Sichania in Mongolia. These were heavily armored with massive clubs and intricate patterns of osteoderms. In contrast, Gondwanan ankylosaurs were fewer and often less well known, but still diverse. South America's nodosaurids bore long spikes instead of clubs. Antarctica's forms suggest resilience in harsh climates. Zealandia, if it held ankylosaurs, would have added its own note to this symphony of diversity, creating a lineage suited for damp forests and isolation. The ecosystem of Zealandia must be painted more fully to understand their place. Picture forests of Araucaria and podocarp trees, tall and ancient, their branches stretching into a sky filled with pterosaurs. Beneath them, cycads formed thick groves, ferns carpeted the floor, and flowering plants spread in patches. Rivers wound through valleys, carrying sediments into deltas where fish and amphibians thrived. Theropods stalked among the shadows, sharp-eyed and sharp-toothed, seeking prey. Sauropods grazed on high branches, their necks swaying above the canopy. Smaller ornithopods darted in groups, always alert for danger, and among them moved the ankylosaurs, low, broad and steady, their armor glinting in dappled light. The soundscape of this world would have been deep and resonant. Ankylosaurs may have communicated with low rumbles, vibrations that carried through the ground as much as through the air. These calls kept groups together, warned of danger or expressed dominance. The forest floor would have echoed with their steady steps, the crack of plants bitten, the occasional thud of a tail striking the ground. Against this backdrop, the roars of theropods and the trumpeting calls of sauropods completed the chorus. Even their interactions with plants were profound. By feeding on ground-level vegetation, ankylosaurs prevented undergrowth from choking the forest. This opened niches for smaller plants and animals, increasing biodiversity. Their dung carried seeds, spreading plants across the land. In this way, they were not only consumers, but also distributors, helping the forest to renew and spread. They were gardeners as much as grazers, shaping the world in ways invisible yet enduring. The imagery of ankylosaurs in Zealandia can be pushed further by comparing them to the moa of much later ages. Just as moa filled niches in New Zealand as large herbivorous birds, ankylosaurs may have filled similar roles in ancient Zealandia, slow but constant shapers of vegetation. Both were relatively defenseless against humans or absent predators. But while moa lacked armor, ankylosaurs carried fortresses on their backs. This contrast shows how evolution in different times produces different solutions, even when the roles are alike. As the Cretaceous wore on, Zealandia's fate changed. Rising seas flooded much of its land, isolating patches as islands. Ankylosaurs, if they lived there, would have been squeezed into smaller habitats, their populations dwindling. Fossils buried in these shrinking lands would later be submerged, leaving only rare traces on the margins. This may be why their remains in Zealandia are so rare today. Yet even fragments remind us that they may have endured there, guardians of a land now mostly lost to the waves. To compare them again with their Laurasian cousins, consider the sheer size of Ankylosaurus in North America. These giants weighed over 6 tons, their armor thick as stone. In contrast, smaller forms like Minmi from Australia were only about 3 meters long, with lighter armor but a similar defensive strategy. If Zealandia held ankylosaurs, they may have resembled Minmi more than Ankylosaurus, adapted for dense forests and limited space. This would place them among the smaller armored defenders of the world, but no less significant. Their survival strategy was not size, but defense and endurance. The study of ankylosaurs is a study in contrasts. They were peaceful yet formidable, slow yet powerful, passive yet armed. They did not dominate by aggression, but by resilience. In Zealandia, their role would have been the same: to endure, to feed, to shape the forest, and to resist the predators that prowled around them. Their armor was their language, their statement to the world. You may attack, but you will not succeed easily. Even today, when paleontologists uncover ankylosaur armor, they find beauty in the patterns, Each osteoderm is unique, like a piece of natural sculpture. Some are ridged, some smooth, some spiked, some dull. To see a full skeleton of an ankylosaur in a museum is to see nature's artistry and defense. The Dinosaurs of Zealandia, if ever fully uncovered, would add to this gallery of natural armor, showing designs never seen before. Duck-billed dinosaurs, the creatures known to scientists as hadrosaurs, were among the most fascinating plant-eating animals to ever walk the earth. Their bodies were built in ways that made them both powerful and adaptable, and the remains they left behind have told researchers remarkable things about how they lived, how they moved, and even how they may have traveled across great distances. These dinosaurs are called duck-billed because of the flat, wide shape of their snouts, which looked very much like the beak of a duck. This feature was not only unusual, but also highly useful, for it allowed them to crop plants easily and feed in ways that many other dinosaurs could not. When paleontologists began to discover their fossils in different corners of the world, it sparked many questions. How could such similar dinosaurs appear across regions separated by enormous distances of land and water? The answer that began to take shape was migration. These duck-billed dinosaurs may have been great wanderers, moving across ancient landscapes in search of food, suitable climates, and safe places to raise their young. The fossil record, scattered across continents, became a silent map of their journeys. Hadrosaurs lived during the late Cretaceous period, around 75 to 65 million years ago. This was a time when the continents were arranged differently than they are today, and when climates were warmer and seas stretched far inland. They grew to impressive sizes, with some species reaching lengths of up to 40 feet and weights that could rival modern elephants. Their large herds would have been an unforgettable sight. Rivers of life moving across plains, their duck-shaped mouths busy cropping plants, their strong legs carrying them forward, and their long tails balancing their massive bodies. Fossils of hadrosaurs have been discovered in places as far apart as North America, Europe, Asia, and even Antarctica. This wide distribution suggests that they were able to adapt to many environments and climates. In North America, for instance, their bones have been found from Alaska down to Mexico. This north-to-south range gives the strongest clues about migration. Fossils of juveniles, eggs, and nesting grounds have been found in the far north, in places like Alaska, where the climate during the late Cretaceous would have been cool, though not as icy as it is today. That meant hadrosaurs may have raised their young in the north during the warmer seasons, then moved south when the harsh winters approached. Migration in dinosaurs is a subject that fascinates scientists because it shows that these animals may have behaved in ways very similar to some modern species. The comparison is often made with caribou or wildebeest, which migrate in vast herds across great distances to follow food and favorable climates. The hadrosaurs, with their strong legs and efficient teeth, could have done something similar. Their jaws contained hundreds of tightly packed teeth that formed grinding surfaces, perfect for breaking down tough plants. This dental structure allowed them to feed on a wide variety of vegetation, giving them the flexibility to survive in different regions as they traveled. The teeth of hadrosaurs are sometimes called dental batteries because they work together like a machine. As teeth wore down, new ones replaced them, creating an endless cycle of grinding tools. This feature meant that hadrosaurs could process plants more efficiently than many other herbivorous dinosaurs. Combined with their wide beaks, it gave them the ability to exploit almost any plant-rich environment they entered. This adaptability could have been a major reason why they were so successful and why their fossils are found over such vast ranges. The remains of hadrosaurs do not only reveal where they lived, but also how they lived. Some fossil sites have preserved entire herds buried together in floods or volcanic events. These mass deaths show that hadrosaurs traveled in groups, much like modern herd animals. Living in herds offered protection against predators, for large numbers made it harder for meat-eating dinosaurs to single out individuals. Moving together also made migration more efficient, as groups could share knowledge of routes, food sources, and nesting sites. Evidence of nesting sites has been particularly important. In places like Montana and Alberta, fossilized nests containing eggs and hatchlings have been uncovered. These discoveries reveal that hadrosaurs returned to specific locations to lay their eggs, much like modern birds and turtles. The nests were often grouped together, suggesting that whole herds returned year after year to the same safe grounds. This return to nesting grounds is another form of migration, a seasonal journey driven by the need to reproduce in familiar and favorable places. The hadrosaur young discovered in nests often showed signs that they stayed in the nest for some time, cared for by adults. Their legs were not yet strong enough for long migrations at birth, which means the adults may have remained with them until they grew strong enough to join the herds. This implies a complex social structure, where migration was not only about finding food, but also about ensuring the survival of the next generation. In Alaska, bones of hadrosaurs have been found in abundance, sometimes forming bone beds with thousands of individuals. Scientists believe that these herds lived in the far north during summers, when plants grew rapidly under nearly constant sunlight. But as winter approached, the sun would disappear for months. Temperatures would drop, and food would become scarce. For a plant eater depending on fresh vegetation, this would have been disastrous. The solution was migration. The hadrosaurs likely traveled southward to escape the harsh winters, then returned north when conditions improved. The distances involved in such migrations would have been immense, hundreds or even thousands of miles. But the anatomy of hadrosaurs suggests they were capable of covering these distances. Their strong hind legs allowed them to walk for long periods, and they could also move on all fours when necessary. Their large herds would have made the journey safer, as predators were less likely to attack massive groups. Interestingly, some scientists have debated whether hadrosaurs really migrated such long distances. Another possibility is that they were able to survive the northern winters without leaving. The climate millions of years ago, even in the far north, was warmer than today, with forests and rivers that may have provided enough food. Some researchers argue that hadrosaurs may have adapted to cold conditions, perhaps hibernating or slowing down their activity when food was scarce. However, the evidence of widespread fossils across regions still strongly suggests that at least some species undertook seasonal migrations. The global distribution of hadrosaurs also raises questions about continental connections. During the late Cretaceous, land bridges existed that linked continents now separated by oceans. For example, Asia and North America were connected by the Bering Land Bridge, which would have allowed dinosaurs to move between the continents. Fossils of very similar hadrosaurs have been found in both Asia and North America, suggesting that herds may have crossed back and forth over this bridge. This movement spread them across continents, creating a shared lineage that spanned vast distances. The remains of hadrosaurs have also been found in Europe, where they appear to have lived on island chains that dotted the shallow seas of the time. Their ability to adapt to island environments again shows their flexibility and resourcefulness. In Antarctica, discoveries of hadrosaur bones suggest that they were able to survive in polar regions, which would have had months of darkness each year. Whether they migrated in and out of these regions or adapted to stay there year-round remains an open question, but the very presence of their fossils in such extreme places shows their remarkable success as a group. The skulls of hadrosaurs reveal another feature that may have played a role in migration and herd behavior: the crests found in some species. These crests came in many shapes and sizes, some like tubes, others like elaborate helmets. Scientists believe that these crests were used for communication. They may have allowed hadrosaurs to produce calls that could carry over long distances, helping herds stay together during migration. Visual displays may also have played a role in identifying individuals or species within massive moving groups. If migration involved thousands of dinosaurs, communication would have been essential to avoid separation and confusion. The hadrosaur success is shown not only in their widespread fossils, but also in their numbers. They were among the most abundant dinosaurs of their time, and their remains dominate many fossil sites. Their abundance may itself be evidence of migration, for only by moving to follow food and escape harsh climates could such large numbers of animals survive. Their herds may have reshaped landscapes, much like bison or elephants do today, trampling vegetation, spreading seeds, and changing ecosystems as they traveled. Even the tracks left behind by hadrosaurs provide clues. Fossilized footprints, preserved in ancient mud and later turned to stone, show paths that may have been migration routes. Some trackways extend for miles, with hundreds of footprints from different individuals moving in the same direction. These trackways suggest organized, large-scale movement, a hallmark of migration. Studying hadrosaur migration has also shed light on the evolution of social behavior in dinosaurs. Moving in herds requires cooperation, communication, and timing. It means animals must wait for the young, protect the weak, and coordinate movements. These behaviors, seen in modern migratory animals, hint that hadrosaurs were far from simple-minded creatures. Their ability to thrive across continents and adapt to different environments points to intelligence in managing group life and long journeys. In some cases, fossils show hadrosaurs with injuries that had healed, suggesting that individuals were cared for by the herd rather than abandoned. Such care would have been important during migrations, where the loss of even a few members could threaten the safety and knowledge of the group. Strong social bonds may have held herds together as they crossed rivers, plains, and forests in search of new feeding grounds. The study of migration in duck-billed dinosaurs is ongoing, with new discoveries continuing to add details. Each new fossil site adds a piece to the puzzle, showing routes, behaviors, and adaptations. Whether moving between continents across land bridges, traveling north and south with the seasons, or returning to the same nesting grounds year after year, hadrosaurs appear to have been dynamic and mobile creatures, shaping and reshaping the ancient world through their movements. The ecology of hadrosaurs is painted from their bones, their teeth, their tracks, and the traces of their nesting grounds. They were herbivores, animals whose lives revolved around eating plants. But unlike many other herbivores, they had evolved highly specialized mouths and teeth that gave them remarkable efficiency. Their beaks acted like clippers, cutting through leaves, twigs, and grasses. Behind these beaks were hundreds of teeth, arranged in rows and stacked in layers, forming dental batteries that allowed them to grind their food, much like the molars of modern cows. This made them one of the few dinosaur groups capable of processing tough and fibrous plants. As a result, hadrosaurs could feed in almost any environment, from open plains covered with ferns and horsetails to forests of conifers and flowering plants. The variety of plant life they could consume made them flexible in ways that many dinosaurs were not. Other plant eaters, like the long-necked sauropods, could strip branches but had less efficient chewing systems, while armored dinosaurs like ankylosaurs may have been more limited to low vegetation. Hadrosaurs, by contrast, had the ability to chew almost endlessly, breaking down food to extract every bit of nutrition. This gave them the energy to sustain long migrations, to reproduce in large numbers, and to survive across wide geographic ranges. Fossil discoveries show that hadrosaurs lived in enormous herds, sometimes numbering in the thousands. In the Badlands of Alberta, bone beds have been uncovered where countless individuals were preserved together, suggesting they died suddenly during floods or storms while traveling as a group. These fossil graveyards are snapshots of herds caught in moments of catastrophe, but they also reveal the scale of their social lives. Living in groups this large provided both safety and structure, much like wildebeest or zebras on the African savanna today. The comparison to modern animals helps in imagining their world. Hadrosaurs, moving across ancient landscapes, may have resembled great herds of bison once seen on the North American plains, or caribou migrating across Arctic tundra. In both cases, the animals move as a single living river, filling valleys with the sound of thousands of feet, the low rumbles of communication, and the endless motion of bodies bound together by instinct and necessity. For hadrosaurs, migration would not only have been about food, but about survival, reproduction, and safety in numbers. Tracks found in ancient sediments give a clearer picture of their journeys. In several places, paleontologists have uncovered long sequences of footprints stretching for miles. These trackways often show many individuals moving in the same direction, some large, some small, suggesting that whole herds, including adults and juveniles, traveled together. The footprints reveal details like gait and speed, with some indicating slow, steady walking and others showing bursts of faster movement, perhaps as the herd crossed rivers or moved away from predators. The very act of preserving such long trackways means that hadrosaurs followed the same paths repeatedly, much like elephants carving migration routes through the forests of Africa. The nests of hadrosaurs add another dimension to their ecology. In places like Montana, paleontologists discovered sites where hundreds of nests were concentrated in a single area. Each nest contained several eggs, and fossilized embryos and hatchlings were sometimes preserved within them. These nesting grounds suggest that hadrosaurs, like sea turtles today, returned to the same locations year after year to lay their eggs. The presence of many nests close together indicates communal nesting, where whole herds arrive to breed. This cycle of returning to nesting grounds represents another form of migration, one driven not by climate, but by the deep instinct to reproduce in familiar and safe places. Some nests also show that hatchlings remained in them for some time, growing before they were able to leave. Fossilized bones of young hadrosaurs suggest that adults may have brought food to the nests, or at least protected their young until they were strong enough to join the herd. This kind of parental care, rare in reptiles today but common in birds, suggests that hadrosaurs were advanced in their social behavior. Migration in such a setting was not just a physical act of moving across land, but also a social event where groups protected the vulnerable and ensured the survival of the next generation. The climates in which hadrosaurs lived added challenges and opportunities. During the late Cretaceous, the Earth was warmer overall, but the poles still experienced long periods of darkness in winter. Fossils in Alaska and even in Antarctica show that hadrosaurs lived at extreme latitudes. In Alaska, evidence suggests that herds lived in the north during summers, feeding on the lush vegetation that grew under 24 hours of daylight. But as winter arrived and darkness stretched over months, the vegetation would have died back and food would have become scarce. To survive, the hadrosaurs likely migrated south, following rivers and valleys to regions where food remained available. The distances covered during these migrations may have reached hundreds or even thousands of miles. To imagine such a journey, one can think of the caribou in North America, which travel more than 1,000 miles each year between summer and winter ranges, or the wildebeest in Africa, which follow the rains and the grass across hundreds of miles of savanna. Hadrosaurs, with their long legs and efficient feeding strategies, could have matched or even exceeded these migrations, moving in herds so large that they must have shaped entire ecosystems in their wake. Fossils from Asia show close relatives of North American hadrosaurs, suggesting that they crossed land bridges that existed when sea levels were lower. The Bering Land Bridge, connecting Alaska and Siberia, may have been a highway for dinosaurs, just as it was for mammals tens of millions of years later. This means that herds of hadrosaurs could have spread back and forth between continents, mixing populations and spreading their kind across the globe. Their adaptability was so great that they thrived in environments as different as the swamps of North America, the island chains of Europe, the deserts of Asia, and the polar forests of Antarctica. The crests found on some hadrosaurs add an intriguing element to their ecology and possible migration behavior. Species like Parasaurolophus had long, tube-like crests extending backward from their skulls, while others had helmet-like or dome-shaped structures. These crests were hollow and connected to the nasal passages, allowing the animals to produce deep, resonant sounds. Scientists believe these sounds could have been used to communicate over long distances, much like the calls of elephants or the bugling of elk. During migration, when herds stretched across great distances, such calls could have kept groups together, warned of danger, or signaled the start of movement. The crests may also have served as visual signals, helping individuals recognize members of their herd in the chaos of migration.